Good morning, everybody. My name is Bo Hammer. I'm the Executive Director of the Institute for Mathematical and Statistical Innovation at the University of Chicago, and I'll be chairing this session. The session is called the NSF Mathematical Sciences Institutes, Physicists Collaborating with Mathematicians on Major Societal Challenges. We have 5 speakers this morning. Each speaker has 36 minutes for their entire talk, hopefully leaving 5 or 6 minutes at the end for some Q&A. I'm in charge of time, and I'll do my best to keep us on time because that's APS #1 priority, is to keep things on time this week. So our first speaker is Christian Ratsch, who is from UCLA and the Deputy Director, as you can see, of IPAM. Christian.
Okay, thank you, Bo, for inviting me to speak at the session. And am I loud enough, or do I need to move my microphone up or down? Yeah, I'm just asking if it's good enough for everyone in the audience. Okay, so my talk is called Opportunities for Interdisciplinary Collaborations at the Math Science Institutes. And as Bo just said, I'm the Deputy Director at IPAM, so I guess he chose me as the opening speaker because I do represent the institutes from the administrative side. At the same time, I am actually a physicist, so that's why I do this at a physics meeting here. And what I will do in my talk is I have kind of like 2 parts. The first part is just a very general introduction to the Math Institutes, who we are, what's our mission, why do we exist, and how do we do what we want to do. And then this should take like 10 to 15 minutes. And in the second part, I will give some examples of how mathematicians really contributed to what physicists are doing. And of course, that's kind of biased. I will just give examples of what I would call success stories at IPAM, the Institute for Pure and Applied Mathematics. And this is kind of like modular. I will talk about materials design, modeling epitaxy, astrophysics, quantum computing, and electrochemistry, depending on how time goes. So the first question is, why do we have math institutes? And you know, I could give many answers. So here are kind of like 3 bullets why we have math institutes. The first is math is increasingly central to science. And we all know that, you know, modeling and simulations now have come to a point where they actually can make some real contributions and really interface with reality and experiments. There's an increasing reliance on algorithms in general, for example, signal processing, data analysis. And of course, machine learning is everywhere. And math is also increasingly central for society in general. And again, machine learning is everywhere. And when you do machine learning for all kinds of things, questions like privacy, encryption, you know, the fact that you have imperfect and biased data, uncertainty quantification, all these things become relevant. And these are highly mathematical topics that need to be addressed. And therefore, you know, in general, you know, progress depends on developing math tools. And that's, you know, why, as I said, math institutes exist. The NSF recognizes this, and therefore the NSF supports currently 6 math institutes, and I will introduce them in a few minutes and talk a little bit about what we are doing, maybe. Okay, here we go. So there are 6 institutes, and as it happens, we are on 5-year funding cycles, and we need to be renewed. In fact, we all have to write a renewal proposal, which is due a week from now. So I just wanted to mention that. And if you look at the NSF solicitation for the institutes, you see the rationale why the NSF is supporting the institutes. Mathematical science research institutes are national resources that aim to advance research in the mathematical sciences through programs supporting discovery and dissemination of knowledge in mathematics and other disciplines. The institutes help focus the attention of some of the best mathematical minds, fine. And the institutes are also a community resource that involve broad groups of people. And many of the physicists here are probably familiar with the KITP, so as a Kavli Institute for Theoretical Physics in Santa Barbara. So in a way, the math institutes have a similar function, but there's not just one in the math community, but several. And of course, another reason to think about it and to look at it is the physics community, of course, has a lot of facilities, like, you know, experimental facilities like telescopes or accelerators that have, to some extent, similar functions as the institutes. And since the mathematicians don't have these type of facilities, the mathematicians have several math institutes. from the NSF solicitation, just a few facts here. So the deadline is next week, and these awards are for 5 years. The awards are of the order of 2.5 to 6 million per institute. So that actually is quite a bit of money if you think about it. In fact, if we support of the order of 6 institutes again the next cycle, that means that the NSF is actually putting of the order of 12% of the entire math budget just into those 6 institutes. So that gives you an idea for the importance and relevance of all of these institutes. So who are the institutes? As I said, we currently have 6, and I'm going through them here in a little bit to describe these 6 math institutes and try to distinguish them a little bit. The oldest one is Siemens-Laufer at Berkeley, that is formerly known as MSRI, Material Science Research Institute. And I would say, and I hope I'm not insulting anyone when I make personal comments about all the institutes, Simon-Lauder is probably more on the pure math side, and in that sense, probably a little bit less relevant for physicists who want to work in institute. It's also the oldest of the institutes. Then we have IPAM, that's us. I represent IPAM. That's the Institute for Pure and Applied Mathematics. We are 24 years old. We are on the UCLA campus in Los Angeles. And I will tell you a little bit more in the second part of my talk about some of the programs and successes we had. 2 institutes that I think are kind of similar to what IPAM is doing, ICERM and MSRI. ICERM is the Institute for Computational Experimental Research in Mathematics. They're at Brown University in Rhode Island. And IMSI is actually like the youngest of the institutes. That's the Institute for Mathematics and Statistical Innovation in Chicago. Our chair is the executive director at IMSI. And I think IPAM, ICERM, and IMSI are similar in the sense that we are more straddling mathematics, applied mathematics, and applications. And we are also similar in the sense, excuse me, that we have similar activities. We have long programs and short programs. Simon-Laufer also has long programs. I will tell you in a few minutes what I mean when I say long programs. And in contrast, in addition, we have 2 more institutes, AIMS, the American Institute of Mathematics, and the IIS, Institute of Advanced Studies. They do not have long programs, and they're a little bit different. AIM is an institute in Pasadena. They moved from Palo Alto, and they mainly have 1-week workshops, quite a few. In fact, every week there's another 1-week activity. And the IIS is very different, and I think their main contribution is that they support postdocs for a longer period of time. So that's kind of like a brief overview of all the institute, and somehow I'm not able to use this. No, I just slip here and I push the button that's one below, which I'm supposed to push. If you look at the web pages of all the institutes, they all have a mission statement, and if you read it, I think it's fair to say we say similar things, and I kind of like summarize here what we all kind of say what are our goals and missions. As I said, advance research in mathematical sciences, increase the impact of mathematical science in other disciplines. So we're all trying to be interdisciplinary to some extent, more or less. We provide infrastructure for collaboration, sponsor interdisciplinary research. But I also want to highlight the things more at the bottom here of this list. This one expands the talent base engaged in mathematical research in the United States. So we all actually pay a lot of attention to issues like educating the next generation of scientists, having activities for younger people, and focusing on diversity, because I think we all realize that actually diversity is an important aspect in mathematics and STEM sciences in general. So these are, roughly speaking, the goals and missions of the Institute. And then the question is, how do we do what we are supposed to do? And here I have a slide where I say the typical activities at the institutes. And I think most institutes have programs of that sort or some variation of these programs. I think the most important ones are what we call the semester-long research programs. In my next slide, I will describe in more detail what that means. Pretty much all of the institutes also have week-long standalone workshops that are on all kinds of topics. But then, lots of other things. Some institutes have actually postdoctoral visiting positions. Most institutes have undergraduate research experience. That's typically in the summer in the form of some REU or REU-like programs. The institutes have summer schools on certain topics. We, for example, just had a summer school that was in the winter on quantum computing. So we have these type of things. And then the institutes have other activities like professional career and development workshops, targeted workshops, and also public outreach events of all kinds. This slide might be important actually to several people here, so let me explain what I'm trying to show you here. Because who's coming now to all of these activities? Well, if it's a workshop or a program, some people are invited and you just get an invitation and you come and the institutes pay for it and that's it. But then of course there's also a group of people who come to an institute because they they see that it's interesting and they apply to come and apply for funding. And I want to make a pitch here, not just on behalf of IPAM, but all institutes. Check out what all the institutes are doing and consider applying. There is funding available for people at all seniority levels to participate in all of these activities. And I kind of summarized, hopefully reasonably adequate for all institutes, who can apply for what type of program and what is the lead time. So the long programs, which are kind of like the bread and butter and for the most important and impactful activities, these are activities where everyone, graduate student, postdoc, faculty can apply, receive funding. Application deadlines are at least half a year, sometimes a year and a half in advance. And for workshops also, people can apply. For some institutes, the application deadline is rather short, only 2 months, so check out the details. But basically, everyone can apply. So you don't have to kind of know someone who is going to this program or even organize a program to go. You can just look at the webpage of the institutes and of these programs and apply to go to these activities. All right, so here's a list of some upcoming activities that might be of interest to the physics community. And by the way, from now on, I will mainly focus on long programs. I think that's probably most useful, but as I said, there are also one-week workshops. So, and I think I said earlier that among the 6 institutes, Simon Laufer is a bit more pure math, so therefore I'm not really mentioning them here. Then, IPAM, INSEE, and ICERM are a little bit more in the interface between applied math, computational maths, and physics, so therefore I would focus on them here. So at IPAM, we have 2 upcoming programs that are clearly of interest to physicists. Next fall, we have something on electrochemistry, and I will actually talk about this towards the end of my talk in more detail. And then half a year later, we have a program on fusion, so clearly a physics type of physics-inspired program at the Math Institute. INSEE, the institute of our chairman, has a program on data-driven materials informatics. That program actually starts today. And the main organizer of that program is our next speaker, Danny. He will probably say something about this program later. And then in the fall, INSEE has another program on quantum information sciences, which of course is also highly important and interesting to the physics community. ICERM doesn't have any long programs, as far as I can tell, that are particularly relevant for physicists, but they have some workshops in the next year that people might be interested in. There's something here in, I guess, astrophysics, and then something on quantum mechanics. So, and I think the best is to look at the webpage of mathinstitutes.org. That is a link to all the institutes, and you can see what the institutes are currently doing and are doing in the future. Most of us have listed activities for the next 2 years or so on our web pages. Okay. I said several times that I want to focus mostly on the long program. So let me tell you a little bit what a long program is like, what I mean when I say we have long programs. And I described what a long program at IPAM is like. I think at INSEE, to some extent, it's similar. There are clearly differences, but it's anyway, let's just say that broad pictures, they are similar to what I'm going to tell you here. So a typical long program at IPAM lasts 14 weeks. It's either in the fall or in the spring. And we have of the order of 40 to 50 core participants. With core participants, I mean people who come to IPAM for the entire long program, meaning the entire 14 weeks. And people who come, they get a lot of support. Everyone gets an office at IPAM, so you can really be at IPAM for the entire time. It's a sabbatical, and sometimes people actually use their sabbatical. Sometimes they just rearrange their teaching, all kinds of mechanisms. When they come to IPAM, there are a number of organized activities. we have what we call tutorials, and then we have 4 one-week workshops that are embedded in a long program that are connected to the overall theme of the long program, and we have a culminating workshop. But then there are also weeks between the workshops. We call them the non-workshop weeks, and in those weeks, there are some less formal activities. We call it working groups, seminars, all kinds of things. And this is a picture I want to make here for people who are considering coming to an institute. Often when I try to recruit people to come to IPAM, I hear something like, oh, the 4 workshops sound really great. I come to those 4 weeks. And then I tell them, no, you really want to come. You really want to, excuse me. You really want to come for the non-workshop weeks, because all the important stuff is happening in the non-workshop weeks. Because that's when you really get a chance to talk to all the other people who are there in much more depth and start some new collaborations. Because let's face it, we all know it. If you consider, for example, a typical conference like CIPS meeting, here, we have 2 minutes of Q&A after a talk. If you're lucky, you corner the speaker afterwards for 15 minutes outside. Maybe you're really lucky, you go for lunch and talk a little bit more, and then you say, yeah, we should really work on that. And then you go your way, and that's it. And nothing really gets done the way you want it. If you come to an institute, you spend the time between workshops where you have this unstructured, informal time. That's where you can really get things done and start new collaborations. And in fact, in a slide or 2, I will show you one of our success stories, and then maybe also a few more. So I wanted to make that pitch here. And this is a picture of our collaboration space at IPAM. We also have actually something which we're really happy about. We have a culminating workshop at a retreat at a resort at Lake Arrowhead, and some people here have been here. It's actually a really nice place if you ever come to IPAM to experience that. All right, so that's all I wanted to say, like big picture about the institutes. And now I want to give you some examples about things that happen at the institutes and successes where mathematicians really contribute to what physicists are interested in. And I would say the first thing, and maybe one of our most successful and influential things over the last decade or so, started with a program on navigating chemical compound space. That was a program in 2011, so more than 10 years ago. And the motivation was that, chemical compound space is huge. And, some people will argue that there are of the order of 10 to the 60 small molecules, which are defined as molecules that have of the order of 20 or fewer heavy atoms. And I give you some examples of possible molecules that are particularly relevant to physicists at the APS March meeting here. And if you want to study these type of molecules, a DFT calculation, takes off the order of a CPU hour. I mean, some people might argue maybe it's an order of magnitude faster now or this or that, but nevertheless, it's pretty slow. And therefore, if you want to do rational design of materials, you really need very efficient sampling methods, and you really need to have methods where you can calculate the properties much faster than at the DFT timescale. And that was basically the motivation of this particular program at navigating chemical compound space. So now I want to show you one example of what happened in this program. And it's described as this. So, the participants who came to this program had all kinds of backgrounds: math people, computer science people, physicists. And some of the people who came are the authors of this paper here. And I'm here right now. Anatol von Lilienfeld and Alex Tkachenko knew each other before the program, but they had never met before Klaus Robert Müller and Matthias Roth. And Anatol and Alex Tkachenko are what I would call physicists, maybe material scientists, maybe they're chemists, but somewhere like in the physical chemistry arena. And Klaus Müller and Matthias Roth are mathematicians / computer scientists. And we recruited some people to come to this program who came from computer science, who did something which was called machine learning, which nobody really knew what that was in 2011. So people started talking in the beginning of the program. The program started on March 13th. And then these two groups of 2 people each started thinking, well, maybe we can really use this machine learning stuff to speed up our DFT calculation. So they started talking more and more, and finally came down writing down a machine learning model. They used kernel-rich regression, which people used more at the time. Nowadays it's all neural networks, but that's just a detail. The physics people created the test set of the order of, I think, 8,000 or so molecules, and they tested everything. And at the end of the program, they wrote a paper. And in fact, this paper went to PRL, so a pretty We all know what PRL is. And if you actually look very closely, this paper was submitted on June 15th. The program lasted till June 17th. So here we have a case where physicists and mathematicians meet at an institute for a 3-month program, and at the end of that program, before it's over, they write a PRL. And the PRL, of course, here's as a key figure of the PRL, it kind of shows that with machine learning methods, you can calculate the energy of these systems to an accuracy of the order of 10 kcal per mole, which is not exactly chemical accuracy, but it's getting pretty close. And of course, this paper was really influential. It has been cited now 2,175 times. If you actually go to Web of Science and you search for machine learning and density functional theory, how many papers are published in this field? Well, before 2011, it's essentially 0. There are actually a couple of ones here. This is when the program happened, when this paper came out. And then, as you can see, a few years later, the topic has taken off. And in fact, if you look now at this APS meeting here, you want to go to some sessions. It seems to me every other session has machine learning in the title one way or another, right? So maybe I'm exaggerating, but it's something everyone is doing now. And it probably would have happened without the IPAM program. Okay, let's be honest. But I also think bringing together these people from these communities who are now very well respected in the respective communities really had an impact on the development of this field. And now I showed you in their PRL that accuracy of 10 kcal per mole. Now a ton of people work on this. The standard data set is this QM9 data set. And you always see figures like this where people plot the error as a function of the training data. The details are not important. What's important is these are all kinds of machine learning models. Here, these different codes, and you can see if you train it right, you get to accuracy below 1 kcal per mole, which is what's considered chemical accuracy pretty much with all machine learning methods these days. So I think that's a huge success, and it really shows you how the math institutes and physics can get together and advance a particular field in what I would say a very important way. My next example is something which I care about because some of you might know this is actually what I've been doing my own research on for a very long time. I'll try to keep this part short. It's modeling epitaxial growth. For those of you who don't know what this is, epitaxial growth is a process where you deposit atoms on a substrate, and these atoms can move around on the surface. They can form little islands and this and that. And physicists would typically model this by just doing, getting all the rates of all these events and doing a Monte Carlo simulations, and then you go. And when we started talking to the mathematicians, we realized this can be translated into what mathematicians would call a front tracking problem. And that's kind of like indicated here. So this picture is kind of like a copy of this picture here, in the sense that these islands here are now represented by something where all that matters is where's the island boundary. And then mathematicians have techniques to advance the boundary of multiple phases, which translated to this problem is basically the island boundary. And one particular technique that can be used is what's called the level set method that was actually developed at UCLA by Stan Osher, who is a very prominent applied mathematician. And that was also part of this IPAM program on geometrically based motion, which was more than 20 years ago. And actually only have 8 more minutes, right? So I'm going to skip some details here, but basically solving this model ultimately boils down to solving this equation for the level set function and this diffusion equation here for the atom concentration. In this model, we treat atoms not as individual particles, but as a mean field quantities that are described by a PDE. And the point I want to make here is that now we have a set of 2 coupled PDEs, and the extra complication is the boundary condition of the diffusion equation has to be enforced where the eigenboundary is, which is typically not where a numerical grid point is, and therefore you need to have some really sophisticated numeric techniques to do that. And I think this is where, well, I don't want to speak for all physicists, but where physicists are probably struggling, and where being together with applied mathematicians who do this day in and day out really is helpful. And I don't want to say my research field is super important, but I think this interaction between me as a physicist, together with other material scientists, and then the applied mathematicians have really evolved this field using this particular technique to describe epitaxial growth. And it's still an ongoing activities. Many people or groups are doing something similar. Okay, and here's actually a typical simulation from what I just said. So here you see a simulation for epitaxial growth using this level set method. And the important thing is this is not a KMC simulation with particles. What you see here is just a visualization of the solution of a PDE, the one that describes the boundary of all of these items. So that's the point I wanted to make here. Another example, a more recent IPAM program was on gravitational waves. And this was motivated by LIGO experiment and the 2017 Nobel Prize for the 2015 discovery of gravitational waves. Roughly speaking, what this is doing, what LIGO is doing, is LIGO is an interferometer. This is an actual picture of the one in Hanford, where these arms are probably several kilometers long. And what's happening in this interferometer is that you have a light source here, and then you have two beams that are reflected, and then you have a detector here. And when a gravitational wave passes through, the length of one or both of the arms changes, and that changes the signal. So a typical signal is something like this, where there's some sort of signal here, and then clearly something happens. And in fact, this is actually the picture, the canonical picture you see when you Google how do we detect gravitational waves. And in order to actually detect this and to actually describe that this is indeed a gravitational wave, you need to solve some equations. And this is where the applied mathematicians come in again. You need to solve the proper magnetohydrodynamics equations to solve these equations to get your comparison signal. I think one of these colors in here, which I can't read, is actually a simulation, not the real signal. So you really need to compare it to some simulation to say that this is indeed a gravitational wave. Another thing where mathematicians are relevant for this topic is shown here, because the real LIGO signal doesn't look like what I showed you in the previous graph. It looks more like this. Okay, it's a big mess. And if you actually analyze this data properly, the big mess is actually the signal that's shown here. In order to extract this, you need to use some techniques that the applied maths community is very well familiar with. This is like image processing, denoising, machine learning. This is all what's going into detecting actually this signal here that you really can do something with it. So that's that. Okay, that's 2 more minutes, right?
You have 3 minutes.
Okay. I have 2 more examples, so I'm going to speed up the next one. Actually, it's a short one anyway. Another one where I think physicists at the math institutes should be very happy is quantum computing. I mentioned that IMSI actually will have a program, I believe, in the fall. IPAM had a program on quantum computing this previous fall. Clearly, that's where physicists and mathematicians should talk to each other, right? Because the physicists, they think about the qubits and how to produce these qubits. The mathematicians, then focus on the algorithms that we need to use these quantum computers. And by the way, one thing I found really interesting is error correction is also a really important mathematical subject within quantum computing. And I learned in one of the talks at this workshop that if you have of the order of 10 to the 6 qubit, of the order of 90-some, I think 99% of the computational power has actually to be used for error correction, because these qubits are that stable or unstable that you need to do that much error correction. And that's clearly something where the people who do error correction, the math people and the physicists who can think about how can we make these qubits a little bit more stable, really need to talk to each other. So this was a workshop where, a program where, for example, in one workshop we had Peter Shor and Michael Friedman at the same workshop. So Peter Shor, obviously everyone knows he's Peter Shor, the Shor algorithm. Mike Friedman, Fields medalist who works on topological quantum computing. So I think these type of activities are very useful for physicists who are, for example, in quantum computing. Okay, in the last minute, 3 minutes, 2 minutes, I talk about one more example. Actually, I'm going to do this really quick. Electrochemistry. The reason why I want to describe this example is because that actually is an upcoming program at IPAM in a year and a half, and people might interested in this. And now I'm going to describe the science really, really quick. In electrochemistry, you basically have two electrodes with a solvent in between, and there's a potential. And it turns out that the voltage drop all occurs very close to the interface rather than homogeneously throughout the space between the electrodes. And that can be described, that's important because a huge drop in the voltage leads to huge electric fields, and electric fields can drive the chemical reactions. For example, what's shown in this simulation here, oops, I'm sorry. Oops. Sorry. Okay, maybe I won't show the movie. Oh, there we go. Okay. I mean, this shows you that, in electrochemistry, how, for example, an atom can detach from a surface. And the reason this detaches is because the fluctuations in the electric field are so strong, makes the electric field so strong that this detachment process happens. And what that means is, if one thinks about it, that fluctuations and noise are really important to describe electrochemistry. And that is not captured anymore by the classical PDEs that people have developed in the past for those type of processes. And this is why we actually need new approaches. And these people are proposing, a program where new approaches will be studied that take into account the stochastic fluctuations in charge, density, and potential. One idea is to replace the solvers with surrogate models. And we will have a program in a year and a half, and I wanted to finish with this slide here because that shows you again, what type of people come to these activities at the institutes. We have 7 organizers for this program. We have 3 people who represent the mathematics community, but then Neugebauer, Hennig clearly represent the physics community. The other 2 kind of represent more the engineering community. So clearly a very broad interdisciplinary team is coming together to study electrochemistry, how math can help electrochemistry. And with that, I think I want to conclude. I showed you, I described and introduced the institutes to you. I've given you some examples of what can happen when mathematicians and physicists come together. And with that, I thank you for your attention.
All right, thank you, Christian. We have about 5 minutes for any questions. If you have a question, please step up to the mic because the session's being recorded.
So you apparently organized these things way in advance. You had some 2026 things. So if a new challenge comes up out of nowhere that we hadn't thought about before, would you insert a new program to deal with a new challenge?
Good question. So I'm only answering the question for IPEM, but I think the others are probably similar. So the lead time for our 1-week workshops is about a year. For the long programs, it is 2 years. In fact, it's 18 and 24 months. Our science board meets once a year. However, if something exciting comes up, we have actually what we call hot topic workshops, and they will be decided upon as they come along. We don't need to wait for our science board, and they can happen as quickly as 5 months. So if you come tomorrow and there's something really exciting and you think we really need to get together, we could make it happen in the summer. But you have to convince us that it's what we would call hot topic workshops. Sometimes people come and they have this, and then the science board looks at it, and we all think, that's pretty interesting, but it can wait a year. So it depends. But yes, in principle, we have this mechanism. We can be very, very quick. And I also would say institutes are different. I think, without insulting them, Simon Laufer, I think, has slightly longer lead times than we have, and I think IMSI and ISO. And maybe one reason is that, let's just say that I think pure math moves a little bit slower than the applied math. And yes.
Hi, I loved seeing that there are opportunities for students as early as undergrads. Do they need to be nominated by their institution, or can they apply on their own? Can you just say something about that process, please?
Good question. So the main activity for undergraduates at IPEN, and I believe at the other institutes, our summer REU. So That's a program that's at IPAM from June 24th to August 24th or something like that. And people can just apply. I mean, you need to fill out an application form. You need a letter. And I mean, that's where you need a letter from your advisor typically. But you don't need to be connected or anything. It's open to anybody. Coming to one of the scientific workshops, that's a little bit different. Typically, we do not take undergraduates because, you know, I think it's a little bit too early in their career. But if for whatever reason it makes sense, we are open to that as well. We also have some special events like the Modern Math workshop at SACNAS and other activities that are specifically geared toward undergraduates. And again, you do not need to be connected to anybody. You need to find it on the webpage and apply.
We have time for one more question. All right, I see none, so let's thank Christian one more time. Thank you. Okay, our next speaker is Danny Perez from Los Alamos National Laboratory.
Thank you, Bo. Can everyone hear me okay? Yeah, okay. Okay, so as Bo said, I'm Danny from the Theory Division in Los Alamos. And the title is a mouthful, but I want to walk you through how my research interacted with the Math Institutes over the last 15 or 20 years, and how contacts with applied mathematicians really changed the way that we do the physics that we're interested in. Okay, so that's an overview of my involvement with the Math Institute. So the first time I went to IPAM was in 2008, and then I attended 3 long programs at IPAM, first as a long-term participant, then I upgraded to workshop organizer, and then finally as a program organizer in 2023. And right after I leave from here, I'm going to go to IMSI for another long program, for which I'm also a co-organizer. So in parallel with this, as Christian said, the Math Institutes organize other activities. So we've been sponsors of 3 REU summer programs. And I'm not sure why this is switching like this. Yeah, 3 REU programs, which is really confusing. So I'm going to point with my hands instead. And 1 conference for undergrads that target underrepresented minorities in mathematics. So what I would like to do is basically walk you through how these activities map onto research events or research progress that have been made in my field. So I'm going to walk you through the top column. It's very small, you probably cannot read it, but what I want to emphasize also at the same time is that as a result of these activities, we really recruited a lot of undergrads, grad students, postdocs through the IPAM program. So you can see a number of postdocs that went on to work with us, GRA students, and even undergrads that we recruited from the RIPS program. So that's something that I'll come back to at the end, that it's really a unique recruiting opportunity to work with the Math Institute. Okay, so I'll start with the first part of the story that goes about how basically through IPAM, a new subfield in applied math and physics was nucleated around some of the long programs at IPAM. So what I'm going to tell you about is the field of molecular dynamics. So molecular dynamics is very simple. It's just the integration of classical equations of motion for atoms. So you basically put atoms in a box, you time step their equation of motions, and you see what happens. So that's a method that was introduced in the 60s, and it's really used all over the place in chemistry, biology, and materials. So since the 60s, of course, we've seen an exponential increase in computing power that we have available. And this has led to much larger simulations that we can do now. So the record is something around 20 trillion atoms that you can simulate with MD. You can do much more accurate simulations, and in great part thanks to what Christian was talking about, into machine learning combining with quantum methods. But the thing you cannot do is very long simulations. And this has to do with how these simulations are parallelized. So if you try to parallelize a small system on a huge machine, you become communication bound. And basically, you're limited by this communication wall here that limits you to, let's say, tens of nanoseconds a day, no matter how big the machine is. So this is a problem, because there's lots of interesting physics that happens at these long time scales. And we really want to be able to simulate in these conditions of interest so that we can predict things like microstructure evolution, for example. So in physics and in materials, when nothing happens in a simulation, typically people just shake it harder. Right? You increase the pressure, you increase the temperature until something happens. And you can learn some things there, but it's very hard to unbias what you've seen to really infer what the material would have done in the conditions you really care about. So this partially changed in 1997 when Art Voter introduced a suite of methods that are called accelerated MD methods that are really designed to increase the simulation timescales. So Art was my mentor in Los Alamos, and I basically joined them to work on these techniques. So the way Art derived this was really based on rate theories, which is textbook physics and chemistry, okay? So this is nice, it works very well, but deep down, it assumes that all rare events are kind of Markov processes. And as physicists and chemists, we're really comfortable with this concept. And in the limit of extremely rare event that is asymptotically correct. But it turns out that when you hang out with mathematicians, they have a very different sense of what a proof or a demonstration is. So what you think as a physicist makes total sense. For them, they're totally skeptical until they actually prove it in what they deem a proof. Turns out that it's hard to do, so it actually requires kind of long-term collaborations to get at these formal results. But I really need to credit Mitch Luskin, who's a mathematician here in Minnesota, and he saw Art speak about these methods at IPAM, and he decided that mathematicians could really contribute to understanding the formal underpinning of these methods. So we met at IPAM with Mitch, Tony, and Claude, who are applied mathematicians in France, and Art Voter and myself, and we started a new collaboration geared towards really understanding the fundamental underpinnings of these methods. So I won't explain to you what each of these methods are, but the key idea of accelerated MD is that if I look at an MD trajectory in phase space, it's a continuous object that basically jumps from a local basin of attraction on the energy landscape and then stays there for a while, and then jumps to a new basin and then stays there for a while, and so on, makes thousands of jumps like this. So in AMD, what we do is we break this down into single jumps. And we say, okay, if we manage to generate proper escapes out of each one of these subregions that I'll be calling states, then I'm going to get my trajectory right at the end. Okay, so we break out the problem into sub-pieces. And each sub-piece is concerned with predicting the first escape out of a domain in terms of where you go and when you go. And we play all kinds of tricks so that we use MD as a computational engine, but we play tricks to squeeze out the information that we need as fast as we can. So this is basically what all of the AMD methods are about. So what we really care about is understanding these first passage problems out of subdomain of phase space into another subdomain. Okay, so the way we do that is by basically considering an abstract domain in either configuration of phase space, and then putting an absorbing boundary condition around it. And then we want to understand, if I start somewhere in the domain, I start some ensemble inside of W, where and when will it first escape the domain, okay? And the key concept that we figured was the concept of a quasi-stationary distribution. So this is a generalization of something like a Boltzmann distribution, which basically says, if I start a bunch of trajectories inside of the domain and I run for a long amount of time, what is the limiting distribution conditional on not having escape. So I look at everybody that managed to survive for a long time, and that gives me the QSD. And the QSD is quasi-stationary in the sense that if I prepare a distribution according to the QSD, run forward, and then condition again on staying inside, I'm still left in the QSD. So it turns out that the case we analyzed with Tony, Claude, and Mitch was the case of overdamped Langevin dynamics. And there you can do a spectral decomposition and figure out that the QSD is an eigenfunction of your generator that's related to the smallest eigenvalue. And what you can derive with the Fokker-Planck equation is basically that this conditional distribution at long times is the QSD plus a term that decays exponentially fast as a function of what we call the spectral gap. So these are the two smallest in magnitude eigenvalues of your generator. So what this is telling you is that no matter what initial condition you start with in the state, if you run for a while, and a while being something like the inverse of this guy over here, you're going to land in this QSD distribution. So what we were able to prove with our mathematician colleagues is that the QSD is actually unique. No matter where you start, you're going to land in the same distribution. You converge exponentially fast to the QSD, as I showed you. And then you can show that from the QSD, the next escape process is actually a Markov process. So you get out with an exponential time, and the escape point and escape time are uncorrelated to one another. And we were able to show that this is true for any state definition. So it doesn't depend on the specific shape of my state. I can draw any state that I want, and this will hold. Okay, so what does it mean? It means that if I have a trajectory that just enters in a new domain, at short time, it's very hard to describe what's going to happen next, right? It's a very complex condition of exactly when and where I entered in the well. But if I condition everything on spending long enough, where now long enough has a very specific technical meaning, then the next escape from that state is a well-defined kinetic process that's described by a rate constant, okay? So that's very nice, right? It shows you actually how the continuous dynamics in phase space actually converges to a Markov jump process that we're used to dealing with. So for example, when Christian mentioned kinetic Monte Carlo, that's exactly what this is, right? But here we were able to show formally how the continuous dynamics actually converge into this discrete process that we're all used to dealing with. Okay, so that's quite, at least for kinetic people. It was one of the first papers where we actually showed how dynamics turns into kinetics as a limit when you start considering rare events that are conditioned on staying long enough in a state. So that is basically the foundation of all the accelerated MD methods, right? Because we deal all with rate theories, you have to show that, I mean, it's kind of, before you can describe a process in terms of rate, you have to actually show that you have a first order process. And this is not trivial to do, and that's what we were able to do with Tony and Mitch. So this really triggered, and don't try to read this, this triggered really a wave of papers from the math community after this first result came out. And something that I learned working with mathematicians is that if you talk to them as physicists with kind of fuzzy, wishy-washy concepts, they don't really engage. But once you can formalize a problem in a very well-defined setting that they have mathematical tools for, then they really latch on to the problems you care about. And this basically showed that after the initial paper, the mathematicians went to work and basically re-derived all of the methods that we derived as physicists, but in terms of very firm mathematical foundations. So I put in bold all of the participants that were at IPAM in the project. So you can see that it's kind of the IPAM participants were the core of a group, and that nucleated really a new subfield, and now we have papers that have 1 or 2 or 3 degrees of separation from the initial core of people that were here. So it really caught on in a way that I didn't personally expect, and has really led to its own little subfield that wasn't there before. So why do we care about these results? As I said, this produced really a formal understanding of the convergence of MD to a discrete process. And that was something that was not available in the literature, and I think is very, very valuable. And we generalized this formalism recently with another IPAM participant from 2017 to generalize it to an even more general set of discrete process, so semi-Markov processes. So this is also something that is still a fertile avenue of research. What's even more interesting is that it let us state in very general terms what other types of problems could we apply our methods to beyond just molecular dynamics. So it turns out that if the QSD exists, it's unique, and you converge quickly to the QSD, then any dynamical process could be sped up with the tools that we developed. So the first paper we had on overdamped non-homogeneous dynamics is like a 40-page paper. Maybe on a good year, I could have derived this myself, maybe not. But if you want to show this for something like a general non-homogeneous dynamics, that's a 150-page paper of extremely technical work that certainly I wouldn't have done myself in my group. And these are results that really came from, as I said, formalizing the problem in a way that mathematicians understand and can start building on. Okay, so that's a main point here, that by really interacting with mathematicians on a daily basis, we were able to establish a common language, and that led to this new subfield. Okay, so that's the first part of my journey with the Math Institutes, basically going from 2007 to 2017. And then in 2017, there was another long program at IPAM, where we basically built on the foundations that came from the 2012 program. So what we did here is basically build on these foundations to step up into the chain of scales, going from molecular dynamics, that's at the bottom here, all the way up to continuum scales. So if you've seen cartoons like this many, many times over the last 20 years, this idea of multi-scale modeling, it's a very powerful idea, but when you sit down and do it yourself, you see that it's extremely tedious to do simulations at all of these scales, figure out what information do I need to pass up, what simulations do I need to do, what are my uncertainties. So this is something that we wanted to streamline by using more formal statistical tools. So basically what we want to do is to go from molecular dynamics to KMC to reaction diffusion type equations. So in the first part, I basically told you that now we understood formally exactly how to take this first limit here. So the goal in the second program was to understand, okay, now we understand it formally, so how can I turn this into a numerical method that would be computationally optimal in order to extract as much information as we can from these systems to bridge the scales in a way that's totally information-driven and not based on our own intuition. Okay. So the way you bridge, you use molecular dynamics to infer a Markov chain, naively is very, very simple. I start from some state that I know about. I just run dynamics. At some point, I'm going to leave. And if I jump to a state that I've never seen before, I add it to my list of states, use my favorite rate theory, compute the rate, and just repeat over and over, right? And then I'll grow a chain of states that I know about connected by transitions that I've discovered by doing MD. There's a few issues or questions that you have to answer in order to turn this into a real numerical method. Once I start knowing about many states, I have to decide where do I invest my computing power. I have to allocate my work to different states. So how do I do that? Second question is, let's imagine that events are really rare. I'm going to run forever without seeing anything. So how can I optimize this part? And finally, what can I say about the quality of the Markov chain that I will have produced by this process? And this is really key because the systems we care about basically have an astronomical number of states and transitions. So you're never going to find them all. So what we wanted to do is to quantify just how good the model is and use that as a figure of merit to numerically optimize the generation of the model. So for example, what we derive first is a local measure of quality. So imagine I run molecular dynamics for a while. I see some number of events. Can compute the rates for all of these things and sum them up. I'll get something that I call the observed rate. So it's the total rate for everything that I know about. but I know that I'm missing things, right? So the difference between the total rate that I don't know about and the observed rate that I know about is what we call the unknown rate. So this is a local measure of completeness. If the unknown rate is 0, I know everything. If the unknown rate is very high, I have really no idea of what should be happening next. So what we did is to start using statistical tools to derive a Bayesian estimator that will tell you what's the likelihood that your total rate be such and such, given the sequence of waiting times that you had to wait for new things to happen. And the logic here is that by definition, the unknown rate is the rate at which new things that I've never seen before would pop up, right? So you can see that in the waiting time for new things to happen, the information about the unknown rate is hidden in there. So what we did was basically formalized a Bayesian theory of how to estimate the total rate or the unknown rate as a function of the sequence of first passage times that are all the way at the left over there. And what you get out is a posterior that tells you how likely it is that you're missing some amount of your total rate out of the system. Okay, so that's a local measure of quality. So now I have a local figure of merit. I want to make the local unknown rate as small as I can, as fast as I can. So that brings to the second question. All of that theory relies on having first passage times for new things to happen. If I run and nothing ever happens, then I'm acquiring information really, really slowly, and that's not good. So what we endeavor doing is to say, okay, how can we speed it up? And as I said in the beginning, what we did in 2012 was study these accelerated MD methods. So it makes a lot of sense that this is what we're going to use to speed this up. So without going into the details, the method we used is called temperature accelerated dynamics, or TAD. And the idea is very simple. So as I told you in the beginning, if nothing happens in an MD round, everybody raises the temperature. And things will happen faster at higher temperature, but they will happen in the wrong order and also on the wrong timescales, right? So what TAD does as a method is basically take a sequence of first passage times at high temperature and convert them into a sequence of first passage time at low temperature, which is the conditions that you really care about. And again, to do this translation, you use rate theories that we understand better now because of the work that I described earlier. So as of now, just think of it as some black box which takes dynamics at high temperature and generates a statistically equivalent dynamics at low temperature from that information. So the idea is that you're just going to have to run a shorter amount of time at high temperature to extrapolate to long time behavior at low temperature, and then I can stick my sequence of first passage times here in the estimator that I told you about before. Okay. So at what temperature should I run? At first, you might think, well, I just run as hot as I possibly can. I'm going to see all the events very, very quick, and I'll be really happy. But in reality, it's not so simple, because every time I see a new event, I have to do some work on it to figure out what's the rate, what's the time at low temperature, and that costs computation to do this. So if I run too hot, I'm going to go over crazy high barriers that contribute nothing to my rate at low temperature, but I have to pay for it every time. Okay. If I run too cold, then nothing is going to happen, so that's also not good. So it turns out that there's a sweet spot in between, and that's something we derived when we were at IPAM, that corresponds to what's the temperature at which the unknown rate in a given state decreases as fast as possible with respect to total computational costs. So how much MD do I do? How much barrier search do I do? How much of all of the overhead do I do? And it turns out that you can derive the closed form expression for this, but it tells you exactly at what temperature you should be running to extract as much information as you can. And this is very state dependent. Depending on the distribution of barriers out of every state, you'll get a different optimal temperature that really depends on the distribution of barriers. So by doing this, you basically, for every state, you go through that equation here, you figure out what's the optimal temperature at which you run at, and now in every state, you have a personalized optimal temperature that maximizes the information gain. Okay, so now we just have one question left is, now I have many states that I discovered. I know up to utterly run in each one of these states, but now I have to decide in which state should I be running, right? If I know about 1,000 states, where do I invest my computational effort? Well, this again will make use of our unknown rates that we introduced before. And a very nice property of incomplete Markov chains is that if I have a chain and some links are missing in the chain, but I know what the total rate is for these unknown events, it turns out that if I simulate the trajectory on that partial chain, the trajectory is exact up to the point where the simulation would want to select an unknown transition that I've never seen before, okay? So the amount of time that, that a simulation spends in the model before it wants to jump out is a figure of merit that we call the residence time. So how long can I run before something that I don't know about should be happening statistically? So we can estimate the residence time for a big Markov chain, and again use this as a figure of merit, saying that's the thing I want is to make some predictions on very, very long time scales. So I need a model that's able to predict over long time scales. So how do I do that? I do a giant chain rule to this objective function here that tells me how to assign information. And this is, again, something we figured out at IPAM as part of a working group that basically says that the optimal thing to do is not to run uniformly everywhere or to run so that the unknown rate is the same everywhere. The optimal thing to do is to allocate your resources as a function of this complicated thing here, which on the left, it tells you how easy it is to decrease the unknown rate by putting more effort, which makes sense. You don't want to waste your time in states where you're going to get low return. But it's multiplied by this complicated thing here that's a function of the Markov chain itself, which basically tells you how important is this state in the big picture, right? How many trajectories will pass through this state? How long would they spend in this state on their way to somewhere else? So that gives you a sense of how kinetically important the state is, how easy it is to optimally, to decrease the rate if you were to work in that state. And that tells you how to assign your resources. So basically now the idea is that you give me 100,000 cores. I just plug this into the expression, and it tells me exactly how many of my cores should I be investing at each one of the states that I know about to make my model as good as I can, as fast as I can. And these ideas basically led to the third program at IPAM on exascale computing that we had just last year, right? The idea is, if you give me a huge machine, how do I know what to do with it? Like, how can I figure out what's the optimal way of extracting information out of my system without having to babysit the simulations myself? And a method like this is in a step along that direction. So does this mean that I'm in my question period? Or? Okay, perfect. Okay, so when you put all of this together, you get the method that we call Timber, and this again came out just a year after the IPAM program in 2017. So the idea here is that we basically use the fundamental insights that we developed in 2012 and added on top of it some layer of statistics, Bayesian analysis, all kinds of tools from the applied math side and computer science side to actually turn it into a numerical method. So going from basic mathematical insights to really computational techniques that we can use. So that brings me to the last leg of the journey here that basically overlaps between some things we did in 2023 at IPAM and things that we're planning on doing in 2024 at MC. So we have this chain of upscaling information going from MD to KMC to continuum equations. And what we're interested in now is understanding what happens to this macroscale behavior once you realize that the thing you ran your MD with was not exact. So as Christian mentioned, most of what we run MD now, we run MD with are machine learned potentials that are trained to density functional theory, for example. So it turns out that these things are quite accurate, but they're certainly not exact, okay? So you're gonna make some mistake with respect to the quantum behavior, and you want to understand how this will propagate through the whole chain to affect the predictions that you're making on the other end, right? So of course the dream would be to run everything with quantum at this end, but that would be just unbelievably expensive. There's no way we can do that. So what we figured out in 2023 at IPAM again was that these potentials are not perfect, and there's different reasons why they're not perfect. Okay, you might be lacking in training data, so your potential might not be fully constrained. Or you might want to run very, very fast, so you're going to use an approximate form that's not insanely expensive. And that's especially important for us, because we want to do super long-time dynamics with this, right? So now you have a question to ask, is it worth paying 1,000 times more for a marginally more accurate potential? And it's not always clear, right? So what we figured out is that the conventional methods that people use for uncertainty quantification, something like Bayesian regression, is very good at dealing with insufficient data, but it implicitly assumes that the problem is specified, that there is in your ensemble of possible models, a model that's actually exact for the signal you're trying to fit. And when it's not the case, you're actually dramatically underestimating the uncertainties on your predictions. So what we did at UQ with the working group that we had over there, at IPAM, sorry, with the working group that we had over there, is to generalize Bayesian methods for the misspecified case. So if you really push and say, I want a cheap potential that runs very fast, I'm going to make an error, I'm going to have to live with it. How can I bound my errors? So we basically used cross-entropy concepts and generalized the usual Bayesian regression method in order to get confidence intervals on everything that we compute, like transition barriers and other properties that we care about. So we just submitted that preprint a few months ago that addresses this. So now we have a better handle on, if I make a prediction with my model, what are the error bars that I potentially care about? And what we want to do next is basically figure out how can I propagate this uncertainty to the whole chain that I told you about. Right? I want to be able to make statements about a confidence interval on my final prediction that went through this whole chain of upscaling. And this is something that we're going to work on at IMSI. So our program at IMSI is on materials informatics, so we'll have a lot of experts on machine learning, but also on material science, atomistic simulations. So these kinds of questions are really ideally suited for an environment like this, where you need both domain expertise, but you also need to understand uncertainties, statistics, and machine learning at a very fundamental level. Okay, so that's where I'll wrap things up. So as you've seen, I've been involved with math institutes for a long, long time, so since 2008. And I think what impressed me the most is what I conveyed in the first part of the talk, that by building this community around a new problem in applied math, it really nucleated a subfield on its own that took a life way beyond just the small group that started developing these methods at Los Alamos. So now it's a thing that has a life of its own that doesn't just depend on us pushing the methods themselves. And this would really never have been possible without an environment like the institutes. Also, now I have a fairly significant network of collaborators in applied mathematics, and it's not something that you magically gain by going to APS, for example. Knowing the right person that's really interested and has the formal tools to look at the problems you care about is something that's very important, and that's something that came out of this very long-term interactions with the math institutes. And now, through that network of collaborators, I get invited in all kinds of conferences that wouldn't go otherwise. I teach classes as the physicist on duty to mathematician conferences. So I spent sabbatical in math groups. So again, this is not something that would have happened without having the opportunity to interact with mathematicians on a long-term basis. And my last point is on recruiting. By spending 3 months at an institute, working with students, postdocs on a day-to-day basis, you really get to know them in a way that you would never by just interviewing them for an hour. Right? So we recruited a large number of students and postdocs through this that brought expertise that our group doesn't have. And I think that brings a lot of value to my research that I wouldn't have otherwise had. So I just want to finish by acknowledging the staff at IPAM and IMSI that make this possible. They really go out of their way to create environments that make it easy for us to collaborate across disciplines. And I think it's really valuable, and I would encourage everybody here to try to engage with the Math Institutes if they can. Thank you.
Danny. So I think we have time for 1 or 2 questions. I've got one. So I'm a physicist also. I work at a math institute now. And so I'm curious from your perspective, what was your process to be able to speak the language of mathematics and establish these productive collaborations with them to build credibility?
Yeah, that's a very good question. So the first meeting that I described in the beginning with Mitch, Claude, and Tony was basically a 3-day thing, where the first day was just us talking past one another and saying the same things in a different language but not understanding each other. Then on the second day, okay, it starts to make sense what they're saying, and they can understand us, we start to understand them. And then on the third day, we left with a research plan. And it really took 3 days, right? So it's not something that, as Christian was saying, that you have a casual discussion in the hallway that can happen right there. You really have to sit down, establish a common language, and agree on what questions are important. What we think is important, often they don't care, and same in the opposite direction. So just finding the intersections of what they're interested in and what we're interested in is something that takes time. So I think that being in an environment together for months and being able to interact over coffee break or things like that, that's really where these interactions happen.
Okay, thank you. Any more questions? Yeah, come up to the mic, please, real quick.
Yes, I see Los Alamos National Lab. I immediately think nuclear weapons. Very little else I think about when I think about Los Alamos. So are you actually looking at materials that are involved in nuclear weapons on this long dynamic thing? I know people are worried about plutonium and how it behaves over decades, plutonium that goes into nuclear weapons. Can you speak to that?
Yeah, I don't personally. I really work on the open side of the lab. So we do nuclear stuff, but on the civilian nuclear side, so nuclear fuels, materials for fusion reactors. So we do care a lot about extreme conditions, but personally it's for civilian applications. But for example, fuel performance in nuclear reactors is really controlled by long-time behavior, how much energy we can extract from these before we have to store them. So all of these types of techniques are applied to problems in that space.
Okay, I think we're going to have to cut off the Q&A now for our next speaker. Thanks again, Danny. So our next speaker is Kyungjoo Noh from Amazon Web Services Center for Quantum Computing, and let's switch over to tech. You're going to be using your own computer? Okay. Yeah, maybe hook it to the right side. Yes.
All right, can everyone hear me okay? So yeah, thanks so much for the introduction, and thanks a lot for having me this opportunity to speak to the quantum computing and how math can be helpful in studying the quantum computer. So in this talk, I'll be representing to some extent this IMSI workshop on mathematical methods for quantum hardware, and I'll maybe briefly walk through what this workshop was about, how it felt like, and what kind of activities that we were interested in academically out of this workshop. So this was a workshop that happened about 2 years ago in July of 2022. And in this workshop, we had many theorists who are interested in understanding a very sophisticated behavior of quantum devices and how we might mathematically or numerically understand them. And I'll talk more about what exactly is the current theme in the field, but before that I would maybe briefly remark that in this workshop, this was a week-long workshop, and we had exactly 12 speakers who are from diverse background, 3 of them from industry like myself, and 9 of them from academia. Most of these were theorists, and we had more than 50 participants who are engaging with many interesting discussions during this workshop. So that was a very nice experience, and in particular, the schedule was kind of well planned in the sense that in each day we had either 2 or 3 talks, so we were learning the new trends and the things that people are thinking about, and then in the remaining half day or something, we had ample time to have discussions with other participants, and some might have pulled it off to make papers, but I mean, it was a very lively environment, and it's very much enjoyable. So with that, I'll switch the gear a little bit, and then maybe walk through some of the themes that are emerging. So already in the previous talks, we touched upon some ways in which mathematics can help with the field of quantum computing, and one of the examples was, as discussed in the very first presentation here, is, for example, the relationship between quantum error correction and information theory, Shannon theory, and some of the underlying mathematics, coding theory, etc. So these are one of the things that are very exciting. But I also wanted to share another aspect of how math can help with quantum computing that are a little more on the lower level physics instead of the upper level abstract information related aspects. So in this talk, I'll be mostly focusing on how some of the low-level detailed physics are impacting the design and execution of quantum computer programs, and how mathematics may be of help in this new emerging space. So hopefully this complements a little bit what was discussed earlier. And the big theme in these days, as the quantum computers get more developed and get sophisticated, is that we encounter processes that were previously just not observable. These processes get more subtle and sophisticated, that we require more sophisticated tools to get to the bottom of these physics. And these are getting increasingly important in terms of actually getting the quantum computer working. So this has many practical implications as well. And that's why we got together to this IMSI workshop, and a lot of theorists like myself were discussing many methods that we are employing to understand these physical processes. And so yeah, I mean, to give some more concrete sense of what the workshop was about, this is one example that I'm pulling from the website. And in fact, if you go to this link, you can kind of see basically what the workshop was about. For about a week, all the talks were recorded and are available on YouTube. So if people want to go back and watch, they can easily do that. And this is a very interesting example. This is one of the basic things that a quantum computer requires. And in this example, I'm showing a very detailed example of how we read out a transmon. And obviously, I'm not going to go into very domain-specific details, but I'll maybe try to convince, what kind of complexity we used to deal with, and what are things that we are now encountering, and how things are getting more complicated and require some more interaction with mathematical tools. So usually the top equation is what we would write out to solve this transmon readout system in the most accurate way possible, at least under some certain level of abstraction. Usually in a textbook or usually as an introduction, people would make a lot of approximations and would reduce a lot of complexities. For example, like a transmon qubit, where in fact it has many, many levels. We would approximate that as a 2-level system, and then we would make a lot of approximations to simplify the interaction between a transmon and a readout resonator. And describe how the readout resonator could be used to read out the qubit. And this is just showing one example where if we properly couple the transmon qubit to a readout resonator, and then if we look at the readout resonator in the right way, just by looking at how the readout is reacting to the fields, we can infer whether the qubit was in the 0 state or in the 1 state. So that's the kind of general feel of how you would read out a quantum computing bit. And this is showing some of the things that the field has started observing in recent years that were not anticipated in the simplified picture. So ideally, if you look at the plot here, there are many dots in the blue circle, and that would correspond to, say, transport in the ground state. And there's another cluster in the red circle that would correspond to the transport in the first excited state, and the green circle being the second excited state, and so on and so on. And these are what we typically should see. So these are the snapshot of what the readout resonator is getting. And basically, by looking at which cluster we are having, we can infer whether the transport was in the ground state, first excited state, et cetera, et cetera. But the thing that people started observing is that in order to make this happen, you would need to drive the readout resonator somewhat strongly. And sometimes, if you're unlucky, this drive can really induce many different processes that you didn't even anticipate existed. And that's the kind of thing that are represented on the upper right corner. So in this case, the experiment was a bit stress testing like how this readout scheme would work, and we're driving the readout resonator perhaps a lot more strongly than was necessary to kind of zoom into this kind of physics. And what's shown here is that we start seeing a lot of dots that are not classified as what we were expecting as ground state, first excited, etc. And what turns out to be happening here is that the drive that we are applying to be able to read out the qubit is actually introducing many undesired resonances and many different processes that you wouldn't get in a simplified model. So in reality, people started seeing many undesired resonances and transitions under the readout, and this really motivated people to look into the actual detail of physics and then get to the bottom of the fine details that were previously unnoticed. And this talk that was featured in this IMSI workshop kind of shows one way in which this kind of study could be done. So obviously, we should start dropping some of the approximations, but the challenge then would be that we would be looking at larger systems, and we might be able to do some brute force simulations, but sometimes you might need to have some more mathematical methods that are efficient and be able to capture the core gist of what's going on here. And in this talk, there was many techniques. There were many techniques that this talk were talking about, and some of the examples were the flow K theory and some of the perturbation theory. Also, more interestingly, there were some, as it turns out these days, in fact, there are many papers in this line where the chaos theory are getting involved, and people try to make some connections to these more mathematical field of expertise. And really, there are many research going on in order to understand some of the physics that are really as subtle as this kind of mechanisms. And that's one of the themes that are emerging these days as the quantum computer gets more sophisticated. So with that, I'll wrap up that part of the example. And then I also wanted to highlight one of the other talks that were in this IMSI workshop is this open source software that's kind of suitable for understanding, for example, this superconducting qubit systems. And this was an effort coming out of the, I believe, Northwestern University, and also a lot of collaborators there. And these days, as things get more complicated, and then and more collaborative environment is needed, we start having some of these open source efforts so that people can get together and contribute to each other's research. So with that, I'll switch the gears and move on to some of the things that we've been doing at Amazon, and how some of the modeling techniques were helpful in getting our programs going forward. So briefly, this AWS Center for Quantum Computing is about building a quantum computing hardware, and we are particularly interested in getting the quantum error correction working, and eventually be able to build a fault-tolerant quantum computer. And we are physically located in Pasadena, California, and we are right next to the Caltech campus. So that's where we are, and this is what we do. And as an example, we have many different programs within our organization, but one of the things that we are interested in is building a quantum computing system out of an oscillator mode by using a qubit that's called the cat qubit. Some of the details are maybe not that relevant to this audiences, but in general, we are interested in having a noise-biased qubit where each qubit is mostly undergoing a phase flip error, and the bit flip errors are physically corrected. So I'm not going to get into all these details other than stating the fact that this is a new type of qubit. People have not very thoroughly studied this type of qubit, and in order to make some of the premises happen, we need to come up with a new type of element in the system, and then there are many processes that were previously unstudied. And this presented us with some new challenges in terms of like the modeling techniques, etc. So these are some of the things that I'll dive into. So again, the exact detail may not be most relevant to this kind of talk, but then at least I wanted to give a feel that because we are looking at a new type of qubit in this specific program, for example, we have a buffer mode that is not present in most of the other quantum computing architectures. And because we're also trying to demonstrate that the error correction can work, we need many of these cat qubits to be coupled with each other, and that means we need many elements that are there to do that work. And we need many of these unit cells that are well connected. So this is not even showing the entire layout of our device. This is only showing a single unit cell and we have many of these unit cells. And this really shows that the complexity that we are dealing with, even at the unit cell level, is quite sophisticated. And in order to simulate, so here I'm showing the bare minimum of what we should include in the modeling, and then in practice we need to introduce more complexities, and even to simulate this exactly is becoming prohibitively hard, and we need more clever methods to be able to work out systems of this nature. And one example is the TensorNet method that I'm going to talk about in the next slides. So usually, this is a very typical scenario where we want to understand some fairly large system that we might be able to simulate with the brute force, but might take a lot of time. But in reality, we might be only interested in a small part of that larger system. So typically what people would do is we take a fairly large system and then we zoom into a very specific part of it and hope that the environment surrounding it is not having too big of an impact on the subsystem that we want to understand. So that's what people would typically do. They would basically ignore everything that's surrounding your subsystem of interest and then hope that that approximation is valid. And the method that I'm going to introduce here, that we have employed is kind of a systematic correction to this simplistic approach. And it kind of looks like this. So for example, let's say we are interested in understanding the subsystem that's in the right middle. The naive approximation that I talked about basically ignores the fact that there exist the surroundings to the subsystem that we are interested in understanding. And for example, what this tensor network method is doing is really simplifying the exact details of the environment. So if we were not to make those approximations, the environment will have exponentially large Hilbert space. And the realization here is that not all of these exponentially many states are actually having an impact to your subsystem of interest. So what's going on here is to really extract the few states in the environments that are actually having a noticeable impact to your system, and then use them to refine your naive approximation that we talked about previously. So this was a method that has been developed in the past decade or two, and we are at a phase where these methods are really having some practical benefits in terms of understanding the quantum computing systems of interest. And so in the most extreme limit, this reduces to the naive approach that we talked about. And again, this really gives us a way to compress the environmental observables and really just focus on the part of the Hilbert space that are relevant to understanding our system. And here I'm just showing some examples of how these are important. The concrete numbers may not be so important to most of the audience here, but then I wanted to highlight that this method has been useful for us to sanity check many assumptions that we are making in the system. For example, we hope that the coupler, when it's in the off configuration, can successfully detach the system of our interest from everything else. And this kind of calculation is really confirming that that was the right assumption that we made, and this gives us more confidence in our modeling techniques. So for example, in the configuration where coupler was supposed to disconnect this cat qubit from everything else, it does confirm that it successfully decouples, and the predictions that were made in a more naive way on the left-hand side does really agree with more sophisticated calculations using this tensor net method. This is perhaps not surprising. And the nice thing about this method, though, is that we can take exactly the same model on the right-hand side and use the sophisticated tensor network method, and can look into other situations that the naive method would require some other dedicated setup. So the modeling on the right-hand side is a more versatile way that covers all different scenarios that we are interested in. We can sanity check with some one-off simulation, like the one on the left-hand side, to make sure that the model on the right-hand side is really doing the right thing. And the most important thing is that this kind of sophisticated modeling really does allow us to look into the cases that we couldn't really understand based on the naive truncation, etc. So this really does allow us to look into cases that are otherwise very hard and time-consuming to simulate. So with this, we can not only understand the cases where the coupler is supposed to disconnect different systems, we can also use this to understand when the coupler is in the on configuration and a lot of subsystems are interacting fairly strongly with one another. So this does really give us more tools, and this really opens up many different possibilities in terms of our modeling capabilities and the design capabilities. And kind of going back to, these were very practical aspects of what we were doing, but kind of going back to the underlying math or the principles as to why this is a useful approach is the relation to the many-body localization, for which there are many mathematical methods to tackle. And the idea here is basically that typically when we build a quantum computer, we want to address a specific part of the system in a local way. So that means, for example, when we have a big quantum processor, and then if we want to address a very specific part of the qubit, we want the local drive there to have impact only in the vicinity of that drive. That means that typically when we build a quantum computer, the individual system is pretty well localized and detached from everything else. And that's where exactly this many-body localization situation kind of fits in. And a lot of people were, from mathematical perspectives, were studying how we would effectively understand these localized systems. And this tensor net method that I was talking about is an example of an effort out of this research interest. So it also means that going forward, as we kind of try to understand more, subtle physics within these big quantum processors, mathematics can help a lot with these this toolkit that has been developed. And for example, there is a growing interest in understanding those quantum computing architectures from the perspective of many-body localization, which then involves even the chaos theory, random matrix theory, etc. So there is more opportunities within this kind of domain at the level of the low-level physics. So that was one part of the themes, and I'll then move on to some other use cases that we have, which is a situation like this. So one of the challenges is that we have a large quantum computing system, but another challenge is that as we try to do more complex things, often we have to apply some drive to the quantum computing system so that the drive can do some interesting, make some interesting effect to our quantum processors. And typically this, as we discussed earlier, even the drive that's there to execute the readout of the transmon qubit can sometimes really show many undesired features. And it's important that we have a systematic way to understand those driven systems. And there's an approach whereby we can take this time-dependent periodic drive, turn that into a fake quantum mechanical degree of freedom, and then have an equivalence between this driven system and a quasi-statically defined equations of motions. And what this allows us to study is we can basically treat this driven system as a quasi-static system and then use a bunch of methods that are well suited for time-independent system, including the tensor network method. The relevance of this is basically that as we go for more complex ways of operating the quantum computing system, more complexities are added, and we can exactly transform this into just a bigger Hilbert space and hope to use some of the other approaches that we've talked about earlier. So this is one way in which the drive can add complexity. So this is showing an ideal case where the drive is doing the intended, the drive is inducing the intended resonances, but oftentimes so this is some other parameter regime where you apply the drive, but then the drive really introduced some extra resonances that we weren't anticipating, but is really interfering with the desired resonances that we engineered. So in this case, we are able to understand some of these subtle impacts because of this mathematical equivalence between the time-dependent drive and these quasi-static systems. And these are some of the things that gain more relevance as we are now able to notice and sense these kind of subtle impacts. So yeah, with that, I'll maybe go back to this earlier general theme. So as the field of quantum computing progresses, we have increasing level of needs in terms of understanding a very large quantum computing system, and also some need to understand a complex driven system. And we are at a point where just doing the brute force numerics is becoming insufficient in understanding what we need. And that's where the mathematics and more collaboration with the mathematician can come in and really help us. For example, a lot of methods, we are in a very early phase of the quantum computing field, so a lot of the methods that we are trying out are mostly heuristics that are somehow motivated by mathematics. So the growing opportunity could be to formalize some of the approximations they were making and try to find some formal math out of some of the heuristics that are now practical. And this was there was a kind of similar thing discussed in Danny's talk, and given the recency of the quantum computing field, this is not necessarily very actively happening, but it starts happening, and there's more opportunities in this domain. So with that, I might conclude here.
We have plenty of time for questions. Yeah, up to the mic.
So first question is, so first of all, thank you very much for the very nice talk. And I was wondering, you showed some plots on flow K theory, on flow K simulations you've done with your system. And how many modes have you considered in this case? Have you considered the whole system?
Right, that's an interesting question. So this shows, I guess, the starting point of an exploration of this nature. So in this case, in reality, we have a highly integrated system that's not just the cat qubit and buffer, has everything else. Mm-hmm. But here we wanted to understand what's happening, first of all, within this small block of systems. So that's a good question. So for now, we really just zoomed into this specific subsystem. But then something that we might be able to do going forward is we can combine this with the tensor network method. So that means we consider really a large part of the system, and some of the systems are undergoing some time-dependent drive. We can turn that into a Hamiltonian that the many-body localization related methods can really tackle, and be able to study what this drive might do to systems that we don't even know that matters. So by combining the first part of the talk, the DMRGX method, with this kind of OK approach, we might be able to study more subtle things whereby the drive here is affecting some other element that seem really far away and have no relevance, but sometimes they would have some relevancy. So yeah, these are some great ways to combine and generalize what we've been doing.
If I can, I would have another question. On the DMRG-X example that you've done at first when you were computing cross curves with couplers off, I was wondering, do you have also experimental fit for those values, or are just theoretical values?
So in our actual workflow, we do definitely benchmark this against the experimental data that we are seeing, and that's what we've been doing. And but in this talk, I'm just presenting the theoretical sanity checks, and yeah, when the time comes, we'll be able to show the agreement between the experiment and theory as well.
Roughly, does it work?
Yeah, roughly.
Okay.
Well enough that we actually count on this to help our design processes, and they do actually make differences, and we have some sufficient predictive power out of some of the methods like this, and yeah.
Thank you very much.
Oh, thank you for your talk. I'm familiar with tensor network methods, but not familiar with cat qubits or photonics. And my question is, what is your target of simulations in this?
Sorry, can you?
What target of the simulations?
So,
for example, just idling error, just simulate idling errors, or apply to qubit gates or something.
So yeah, I mean, in this case, so the really big picture is we have many of these unit cells, and we are implementing an error correcting code so that the errors in each subsystem can be collectively corrected by scale, basically. So that's what we are doing in the bigger picture. And to make the quantum recursion happen, we need to implement some of the entangling gates between, for example, a cat qubit and an ancilla qubit. So this is showing that application whereby we try to engineer an interaction between the cat qubit and this ancilla qubit. And this interaction is mediated by the coupler. And the idea of the coupler is that when the coupler is in the off configuration, we should completely, ideally, shut off the interaction between the cat qubit and the ancilla qubit. And when it's in the on configuration, we want some pretty strong interaction between them. So in this case, for those who know what this means, we are trying to engineer a dispersive interaction between a cat qubit and an ancilla qubit, and we want to be able to show that we can turn on and off this dispersive coupling with this coupler. And the challenge here is, if you naively think about it, I mean, if you really just want to look at the effect of the coupler turning on and off the coupling, you might as well just strip out the buffer mode and also don't care about the readout mode, etc. The realistic challenge is that the existence of the buffer slightly affects the properties of the cat qubit, and also the existence of the readout and the other couplers also slightly affect the properties of the ancilla. So in order for us to holistically account for all these effects, even though the main physics we're interested in is between the cat qubit and the ancilla through the coupler, we really need this larger system in the model, and then have a way to systematically pull in some of these subtle perturbing effects from the surrounding to the main subsystem of our interest. And this method is really showing that no matter which part of the system we are zooming in, this TensorNet method is effectively compressing the impact of the surrounding, and then we can really look into many different aspects of our system just with a single tool, and with great accuracy.
Okay, so you compare the simulation results with the experiment results.
That's also happening. We obviously do the more basic theoretical sanity checks, and we also try to benchmark this against the experiment, and it does typically work out, at least at the level of accuracy that we can currently notice and resolve. So I mean, it does work experimentally as well.
Thank you.
Hi Kyungjoo, thanks for the talk. I have essentially two questions. How far have you been able to go in terms of number of cat qubits for your simulations with the methods you presented? And how far do you think you could go, assuming, I mean, you combine everything in the ideal way? And
Yeah, so that's an interesting question. So when we tried this out, I guess one of the most sophisticated things that we have tried as one of things, so we haven't standardized it, but like just to give you a feel of like how big of a system we were able to tackle is we have one of the unit cells like this, another unit cell on the other hand side. So we have like 2 copies of this. And if you just convert that into the number of qubits, roughly speaking, like there would be like 30 qubit system. There's no way we can very efficiently simulate them without using very sophisticated computing tricks. But we were able to study those systems in order to confirm that the coupler can effectively shut off the effect due to the other part of the unit cell, and then we can like really zoom into this. And in terms of the computing resource needed, this is an interesting part of the this DMRGX method, or the idea of many-body localization. So the idea is that, I mean, if we wanted to extend this to the entire repetition code, not just like 2 unit cells or more unit cells, the idea is that the extra overhead is polynomial in the size of the system. And the reason for that is basically what we need to be able to capture is the non-trivial correlation that's present in the system. But ideally, when you have a large, quantum computing processor, you have some non-trivial correlation within each unit cell, but the idea of like scaling this up is hoping that different unit cells don't talk to each other. So somehow if you manage to simulate this unit cell of your interest, patching this together and extending this to larger processors is a more straightforward generalization. So that's the kind of idea. So the trick here is to manage to simulate the non-trivial part of the system and then try to find a way to patch it.
Thank you. So Amazon Web Services is a profit-making entity, okay? We're talking about NSF-funded mathematical institutes. So do you actually have to pay to go to these institutes' workshops, or I think you should if you don't? Thank you.
At the time, I was offered to be supported by the program, and in my case, I mean, my employer could support myself. So I mean, I myself, didn't take advantage of that, but I mean, I was offered to get help from the institute, but I decided to not take advantage of it and use my employer's resources to attend this workshop. Yeah.
So I'll jump in there too. So my understanding of one of NSF's motivation is to stimulate economic development and workforce development. And so, as you've noticed from the speakers we've had here, we've had a speaker from the private sector, 2 from academia, and 2 from national labs, so to speak. And as Christian demonstrated, we also bring in people from the entire array of careers, their careers from students all the way up to senior researchers. And so, from our perspective at IMSI, it's really a benefit to bring in people from the private sector at our expense, because it contributes to sort of how mathematicians and physicists can contribute not just in academia but throughout the economy.
If I can maybe add one color to this is from someone from a private sector, an workshop of this nature was obviously important because we get to meet with the academia colleagues and be able to learn some of the academic research that are going on. And this is my impression, and hopefully I think on the other hand side, the academic colleagues sometimes don't have often opportunities to work with some large complex systems, and we bring in some of the problems that we think are important in the current stage of the field. And this workshop was really nice in getting us together and be able to talk about what problems might be interesting, what are going on in the private sector with some complexities that are maybe otherwise not easy to get an exposure to. And we also benefited greatly by engaging with the academic colleagues so that we can also be informed of some of the academic researches going on and really found opportunities to cross-pollinate. And yeah, this workshop did a great job in
All right, thanks for the question. That's a great question, and we're out of time for questions, so let's thank Kyungjoo one more time. And our next speaker is Miranda Cheng from the University of Amsterdam.
Yeah, sure. So, so this thing just stays here, right? It's not some kind of wireless thing. It's some kind of. Oh, okay. Yeah. Yeah. And the clicker is this one. No, oopsie. So, I just click this away. Let's see. And just enlarge it somehow. Control L, and then L. Okay. Ooh, okay. And so, okay, thanks. Okay, good afternoon, everyone. So I'm going to talk about something about the relation between physics and mathematics. So before I start my talk, I just like to show you that there's been, you know, since eternity, some love-hate relations between physicists and mathematics. So I'm very happy that we have this session here. So hopefully that will bring more love and less hatred. Okay, and then just to illustrate this relationship, I'd like to start with some quotes. So Richard Feynman, wait. Okay, Richard Feynman once said, allegedly, that if all mathematics disappeared, physics would be set back by exactly 1 week. Okay, some mathematicians, like Sir Michael Mattia, wasn't very appreciative of the comment and said, well, unfortunately, that was exactly the week that God created the world. Okay, so that's kind of the nature of the interactions, some aspects of the interactions between math and physics. And a few words about myself. So I'm kind of like non-partial in this interaction because my paycheck is, you know, half of the time paid by, 50% paid by physics department and 50% paid by the math department. And also, in the past, I don't know, 10 years or so, I mean, I've been participating and organizing 3 long-term collaborative programs at the AIM, the American Institute of Mathematics, each time running for 3 years. So just like Danny said, I had the feeling that, you know, such an institute such as AIM really greatly contributed to my personal career and to the advancement of, you know, the interdisciplinary research between math and physics. So I guess that's why I'm speaking here today. Okay, so in this complicated relation, okay, I'm confused about left and right. Sorry about that. Left. Okay. Between math and physics, I would like to pick out a branch of mathematics that's, you know, a very unlikely candidate to be related to physics. Why? Because when we talk about physics, we think about measuring something to this decimal and that decimal and that decimal. And number 3, on the other hand, is basically a study of integers. So the two can't be more different in that sense. So, okay, but I mean, I hope to convince you at the end of the talk that these 2 things are deeply related after all. So by doing so, well, I'm first gonna say something about math. Okay, so bear with me, physicists. So what can you study about integer? Because, I mean, this is the first piece of mathematics we all learn from a baby to a toddler and so on. We learn how to count. So we learn the integers. So that seems to be very straightforward. However, well, integers can be very complicated too. Let's take the example of this integer equation x to the n plus y to the n equals z to the n. And we're looking for integer solutions. Okay, when n equals 2, famously, we know plenty of examples given by Pythagoras' theorem. But how about n larger than 2? Okay, it took so many bright minds and so much effort and all kinds of modern mathematics to prove that there's actually no integral solutions to such an equation when n is larger than 2. Okay, we'll say more about that later. And then when we talk about integers, not all integers are equal, okay? Because they're prime numbers, right? And other integers are made from prime numbers. So prime numbers are the prime numbers of integers, okay? So if you understand prime numbers, you understand all integers. So we want to understand prime numbers. But prime numbers are infamously hard to predict. Okay, we know like 37 is a prime number, and we could just, you know, do some mental calculation and we conclude this is a prime number. But soon it becomes harder and harder to tell whether something is a prime number without actually checking it explicitly. So there's this, left and right problem again. I'm just gonna use this since apparently I can't tell. Okay. So we would like to know, you know, the distribution of prime numbers, but it's infamously to predict when the next number would be that's a prime. Okay, so here I'm plotting, for instance, pi of So when I click the laser, it automatically jumps as well. That's very mysterious. Okay, so let's talk about the mystery of prime numbers without laser point. So what I'm plotting here is pi of n, which counts the number of prime numbers that's not larger than n. Okay, then you could plot it. It's kind of wiggly, but it's surprising that despite of the microscopic wiggliness, it's kind of looking more and more like a smooth function. Okay, but I mean, this is still an open question. Okay. So why? Well, it turns out that this problem of distribution of prime numbers is also highly related to the zeta function problem. So what's a zeta function? Well, zeta function has a lot to do with prime numbers just because all numbers are made of prime numbers. So you can define it in terms of all prime numbers like this, the first equation, and it's equivalent to the second equation. No? Okay, just basically a sum over reciprocals of all integers to some power s, and this is an infinite sum, and that defines the zeta function. So zeta function in this definition is explicitly convergent when the real part of s is larger than 1. And also famously, it can be analytically continued to all over the complex plane. So for instance, maybe you still remember that when you're taking your quantum mechanics, when you compute the ground state energy, then all of a sudden you're, confronted with this equality like 1 plus 2 plus 3, etc. is equal to minus 1 over 12. Okay, so the right-hand side is minus 1 over 12 is the same as the value of zeta function at s equals minus 1. Okay, so that's what's called the zeta function regularization of your quantum mechanics problem. So it's elementary to show, I won't go through that today, but it's elementary to show that this zeta function has trivial zeros at all negative even integers. Okay, so we would like to know the analytic structure of this function. So what's unclear is what the other zeros are. Okay, so people have found lots of zeros, at this vertical line when the real value of S is -1/2. So Riemann, at the end of the 19th century, conjectured that all the non-trivial zeros actually lie on this vertical line. So this is such an elementary problem, it seems, and yet I can't think of a more pleasurable way to earn $1 million, and yet nobody has managed so far. Okay, so that's a famous Riemann hypothesis. So it's this zeta function that I would like to take as our vehicle, to go through this journey between number theory and physics. So, well, as we have seen, number theory is beautiful in its deceptive simplicity and yet depth. So that has led Gauss to state that mathematics is the queen of sciences, and number theory is the queen of mathematics. Okay, to be honest, I often feel very uneasy to read about these quotes by male physicists, male scientists comparing their object of study with one female character or the other. So hence, this is my visual rendering of the concept of a queen. I hope you like it too. So fine, we all love the queen of mathematics, but what about physics, right? How am I going to show you that this thing has something to do with physics? So in particular, well, first I would like to give you some phenomenological, proof that these two things are related to each other. For instance, we've got our own journal, and we've got books written on the topic, and then just to the day of today, every year there's new workshops and conferences organized to talk about the relationship between number theory and physics. So something's going on. So I hope in this talk I'll give you a rough snapshot of what people talk about in those meetings. Okay? So what physics? So I will go through different types of physics, from collider physics, black holes, phase transitions, quantum chaos. Okay, so they seem to be completely unrelated. They're not high energy or low energy or condensed matter, but they have something in common. They all have something to do with Riemann zeta function. Okay. So, any questions so far? Yeah. Okay. So first, I would like to then tell you a little bit more mathematics. So zeta function and what's called modular forms. So zeta function, as it's defined here, can be thought of as a Maline transform of an infinite Q series. Okay, Maline transform just takes some Q to the n to 1 over n to the s. And then if you do that infinitely many times over this infinite sum, then you get the zeta function. And so what's the object on the right-hand side? It's called the Jacobi theta function. As I said, it's just defined in a simple way as an infinite Q series. So the coefficient is 1 when the power of Q is an integer and 0 otherwise. Simple as that. And you could quickly convince yourself that it's a convergent function when the size of Q is within the unit disk, okay, when the size of Q is not larger than 1. And we often consider it, as a function of tau, where, Q is just the exponential of tau. And then the constraint that Q has to be within the unit disk is the same constraint that tau has to lie on the upper half plane, defined by the criterion that the imaginary part of tau has to be larger than 0. Okay, so upper half plane has infinite symmetry, okay, in terms of this fractional linear transformation. Okay, so if tau, in other words, if tau is on the upper half plane, then this combination A tau plus D divided by C tau plus D, when this ABCD, has form a matrix of determinant 1, then it's also on the upper half plane. Okay, so that's a symmetry, and especially we're interested in the discrete part of symmetry, SO2Z, where A, B, C, D are integers. Okay, so what is a modular form? for instance, our Jacobi theta function is an example, is a function on the upper half plane that actually embodies the symmetry of the space itself. So in other words, okay, if we map f tau to another function that's defined as f of the transform image of the tau, then these two functions have to be the same up to perhaps some simple factor, okay, numerical factor. So that's a modular form. And modular form actually plays an important role in modern number theory. So since we talked about Fermat, then I might as well say one more slide on Fermat. So for instance, Fermat theorem, we all know that Fermat said that he has proof, but the margin is too small, so he can't write down proof. Okay, but I mean, in the end, right, in the 90s of the last century, like Andrew Watt wrote down finally a proof of this theorem, but you know, his proof contained so much modern mathematics that, you know, it's just hard to imagine that Fermat was not bluffing, but we will never know. So how did Andrew Watt prove that? Well, the idea is assuming that there's a solution to Fermat's equation when n is larger than 2. Then using some modern mathematics to show that there's an elliptic curve and with some function, okay, called the L function. There's some function there, corresponding function here. And then, you know, again, some new mathematics coming out of the last century would say that this function, you know, called the L function, is a Malin transform of a certain modular form, okay? But number theorists have studied their modular form so well, so they have a catalog, and there's nothing like that in their catalog, okay? So it's a proof by contradiction that there cannot be a solution to Fermat's equation. Okay, so that's, for instance, a very important example how modular forms, these functions on the upper half plane with special symmetry conditions, played an important role in number theory. And it's also important because this symmetry is not just a symmetry on the upper half plane, it's a symmetry, also a symmetry of a bagel, okay? It transforms a bagel back to itself, okay? But it transforms a circle to another circle on the torus. So it's like, you know, if you're slicing your bagel like this in the normal way and put your cream cheese and jam on it, and after SL2Z transformation, you're slicing your, you know, bagel in the wrong way, but it's still the same shape. Okay, so that will be an important fact when we encounter physics. So let's switch gear and finally talk about some physics. So near a second order phase transition, okay, what we all know from, you know, physics course is that the correlation length starts to diverge. And hence, length is not an important concept anymore. Because when you measure, you know, some 2-point function with length x, that length gets compared to the correlation length. But if the correlation length is infinite, then that doesn't really matter anymore. So we say that at that point, you know, the physics describing phase transition has scale invariance. Okay, and scale invariance oftentimes get enhanced to conformal field theory, conformal invariance. So phase transition, the physics at phase transition is famously described by conformal field theories, okay? And in this, if your system is two-dimensional, then this symmetry consideration tells you that the partition function will become, a function defined on the torus, and hence has this SO2Z modular symmetry, and will therefore be defined, be one of those modular forms, you know, embodying the symmetry. And then also, here's an interesting fact, practical fact, that, again, number theorists have studied their modular form so well. So, you know, if you have like something basic, if you know something basic about your system, for instance, ground state energy and so on, then you know a little bit of leading term, for instance, of your modular form, and the mathematician can oftentimes give you the full answer. So that gives you the predictive power of modular forms. Just take the simplest possible example, the ferromagnetic phase transition described by a two-dimensional Ising model. Okay, it's famously described by a two-dimensional conformal field theory. And so we're wondering what the partition function is. Well, this first equality on the second line just reflects the fact that it's a modular form, as I said. And then we know it's ground state energy, so we know that it starts with Q to some power, and then we can complete it. And then this power that's of the rest of the terms will then tell you about the spectrum of this quantum field theory, okay? So for instance, the spectrum in this case means the scaling dimensions of operators. We can read that these operators have like dimension 1's and dimension 1. And that gets translated directly to the critical exponents of your phase transitions. Okay, these are the numbers of your favorite alpha, beta, gamma, and so on. So it looks like there are more critical exponents than their scaling dimensions, but we know that the critical exponents have a fixed relation with each other at a given dimension. Okay, so they're so they're equivalent, contain equivalent information. Okay, not just the Ising model, right? These are also, because we have universality, so these are the critical exponents of a variety of phase transitions that's in the same universality as the ferromagnetic phase transition. Okay, so that's one thing. And then the other thing that's maybe more modern are like in the past 20 years, number theorists have been very busy studying all kinds of possible generalizations of modular forms, and there's all kinds of nice adjectives that's used here, like mock modular forms, quantum modular forms, false modular forms, and so on. But it all signals some controlled breaking of the modular invariance. Okay, here, denoted by this dot in that red equation. Okay, a famous example that's probably like by this, probably the most romantic in a way, like his mathematician of the last century, the Ramanujan, or actually 2 centuries ago, more like. So in his last letter to Hardy, right before he died, he talks about something that's called mock theta functions. Okay, and then he wrote down a few pages of examples in this form, given by like infinite sums of some like simple rational functions of simple polynomials in Q. And then he said, like, okay, these are the mock functions, and then they will be important. But he didn't give like any examples or anything. Okay, so mathematicians have been, bang their heads against the wall to try to understand what these objects are. And only in the beginning of this century, like there has been successful modern theory of mock modular forms going on. And right after that, so in this 20 years or so, physicists immediately found a lot of application of such mock modular form in theoretical physics. So what kind of physics? Okay. So let's talk about something that's equally mysterious. There's, hardly any more fascinating objects when you want to tell like high school students about physics these days than black holes. Okay, well, they're cool in many ways, but one of the ways, because it embodies the mystery of quantum gravity. So right now, we still have no complete theory that unifies the quantum physics and gravitational physics. And black holes are where it really matters, okay? Because it's both very small and very heavy. So we expect quantum effects and gravitational effects to be simultaneously very important. So this lack of the theory of quantum gravity causes all kinds of dilemmas. So for instance, there's this mystery of black hole thermodynamics. Thanks to Hawking, we know that black holes evaporate, and the way it evaporates looks like it is some thermodynamical objects. But what are the entropy? What's the origin of this? So what's the quantum states that leads to this entropy? Well, so string theory is a funny thing, right? It gives you a framework where, you know, quantum effects and gravitational effects can be combined together, okay? But I mean, you know, string theory also has its difficulty. You might have heard of like landscape and all that. It sounds all very weird. That difficulty is that it has a very rich inner life, okay? So, you know, in order to understand its behavior in the visible world, we have to understand what it's doing in the invisible part of the world, because string theory says that there's this curled up dimensions that we cannot, as human beings, it's hard for us to observe it directly. So that brings all kinds of problems for string theory, but that's not what we're talking about today. We're talking about the nice things about its inner life, okay? So string theory also says that its favorite kind of inner life is to live with Calabi-Yau for reasons I won't get into today. Calabi-Yau are a special kind of manifolds with symmetries. We will talk more about it later, independent of string theory. Okay, and the simplest non-trivial example of such Calabi-Yau is K3 surface, okay? It's some four-dimensional objects that's very nice and loved and studied by mathematicians and happen also to be very useful for string theory. So in such a relatively simple K3 quantification, then, you know, string theories actually manage to compute. What do they compute? If, you know, in this world, in the visible world, there's a black hole. So what are the quantum states? That's what they could compute. And for instance, in this setup, you could compute that the answer is given by by Mach modular forms, which counts the number of quantum states, okay, at each charge, you know, if you lived in such a universe. Okay, we probably don't, but this is a toy example where you can compute everything and explain in that world thermodynamics of black holes. Okay, and it's also very interesting, like for a mathematician, that this seemingly weird soft breaking of modular symmetry has, in this case, very natural interpretation. Because you could say, like, K3 surface is just not one surface. K3 surface refers to the topology of surfaces. So with a given topology, you could still, you know, change the surface. For instance, if you have a bagel, some shops sell bagel that's a bit larger, it's a bit smaller, a bit, you know, weird shape, but it's still a bagel, right? Because it has this topology. So if you do that to your K3 surface, then quantum states can appear or appear, and that's the origin of the breaking of modular symmetry. So that's very cool. So I would like to advertise that I'm talking about the presence of mathematical objects in physics, but actually there's also a bunch of mathematicians who use physical, you know, inspiration to study mathematics. Okay, so for instance, I will tell you an example of a relation between topology and number theory, and with physics hiding in there. So how does that go? So the key question to study in topology is how to distinguish one object from the other topologically. For instance, if you have like handed a tangle, like your USB cable is like all, but you know, at the end of the day, you can untangle it, right? But if it's an arbitrary knot, you don't know if you could untangle the knot, if it's secretly an unknot or not, right? So that's why, you know, topologists are defined all kinds of topological invariants, and hopefully the topological invariants will be powerful enough to tell you all you need about the topology of an object. So closely related to not is a three-manifold. Okay, so that's a very important question in topology, like to study what kind of topological invariants are there for three manifolds. So for physics, what you could do, it turns out that there's a particularly nice six-dimensional quantum field theory you could consider. And then you could just put it on a closed three manifolds. So 6 minus 3 is 3. So you're left with 3 dimensions. And then you could put it on this, space-time that's given by a cigar, okay, times time. So if you want, it's a solid torus. It's a filled-up bagel. And then the partition function on this side, because of the property of this quantum field theory, will be a topological invariant of three manifolds. You just need to show that this partition function wouldn't change if you change the shape of the underlying three manifold without changing the topology. Okay, but this, three-dimensional space-time, which is solid torus, has a torus boundary. So SO2Z has a natural action on that. So you would expect it to have some kind of residual, modular symmetry. Okay. So in fact, forget about the physics then. You could just discuss the relationship between topological invariance and M3 of three manifolds in the theory of modular forms. So in fact, I was just at American Institute for Mathematics, one of our NSF institutes for mathematics, last weekend on Friday and Saturday, attending a workshop on this relation between number theory and topology. So, number theorists and topologists get together and study this relation, and we could just forget about physics for now. Okay, but without physicists, there wouldn't be such a link to start with. Okay, so that's about, things transforming under SO2Z and all kinds of number theory there and how it shows up in physics. Now I want to switch gear and talk about particle physics. And how am I doing with time? So thanks to, the colliders, okay, thank you. Thanks to the colliders are giving us more and more high accuracy results. So a challenge for theorists is we need higher and higher accuracy predictions from the standard model, okay, in order to analyze data from the collider meaningfully, okay? If you don't have enough precision for your prediction of the norm model, how do you know whether there's new physics hiding in your data, right? So what does that mean? That means that we have to compute the results of more and more Feynman diagrams. But the challenge there is that, well, the usual expansion parameters of Feynman diagram is the number of loops. But just a simple combinatorial fact is that the number of diagrams with a given number of loops grow very fast with the number of loops. So soon, you can't just ask your grad student to compute each loop, right? Or something like that. So it would be very helpful to know the underlying structure of these Beasley Feynman diagrams. So let's study this question and take the simplest quantum field theory as a starting point, as an example. So for instance, let's take the example of massless scalar field theory with quartic interaction in 4 dimensions. So we write down some associated to some graph. We can compute its amplitude, okay? And we want to ask the question, what type of functions they are. So the answer is, a lot of times, the answers are given by special values of zeta function, Riemann zeta function, s equals 2, s equals 3, s equals 5, and so on. And the higher dimensional generalizations called multiple zeta values. And these are nice functions, and moreover, they have the feature that they can always be expressed as some nice iterated integrals. Okay, this is what shows up basically, why they show up, you know, as answers to Feynman diagrams. So that's very nice. It seems that zeta functions, such beautiful functions, is what the answers are. So for instance, you get all these complicated zeta functions for complicated diagrams. And Broadhurst and Kramer at the end of the last century has computed them all. It's like up to 6 loops. And what they found is that they're always given by zeta functions and generalizations. So that seems to be very beautiful, right? These beautiful iterated integrals and zeta functions with, you know, certain, they're all transcendental numbers, but they are zeta functions after all. So it seems like we could get a handle on these. And the question is, are they really all? So the surprise at 8 loop, okay? So it was realized at the beginning of this century that it's not all. You could look at this 8 loop diagram. Things start to break at 8 loops. This is not a zeta function. And moreover, it turns out that you can write it as an integral on the K3 surface, like the simplest color BL that we talked about, okay? So that's just a shocking fact. So now people, well, theoretical physicists are working very hard with the help of number theories, and they have proven some results. So one of them is, for instance, that this, what's called this L loop diagram in the shape of a train track, okay? It's an integral over L minus 1 dimensional Calabi-Yau manifolds, okay? And the latest conjecture is that all amplitudes come from some Calabi-Yau integrals. So I'd like to just pause and take a, you know, broader look at it. It's like, I think that's really what's amazing about doing science. I think, you know, the people like who are designing the colliders or who are doing the data analysis for particle physics and number theorists, you know, wouldn't have dreamt that, you know, it could be Calabi-Yau manifolds, you know, that and the integration thereof that controls all amplitudes coming from such simple 5 to the 4th quantum field series. Okay, I'm basically out of time, and then I would just like to briefly mention the beautiful story coming back to the distribution of prime numbers. So the important thing is that the Riemann hypothesis can tell you a lot about the distribution of prime numbers that's known to just doing mathematics. So people have been studying this pi function a lot. And then in this context of studying prime numbers, and Montgomery has found this observation, okay, that the zeros of non-trivial zeros of zetas tend to repel each other. So during the tea time in Princeton, well, Freeman Dyson heard that, and he said, well, I recognize all these things. I've been studying the quantum system of heavy nuclei. So it's just the same phenomenon. And so he concluded, here's his letter, that the pair correlation function of the zeros of zeta functions is identical with that of eigenvalues of random complex matrices of larger orders. Okay, so this is again a beautiful chapter of, we talk about tea room interactions between mathematicians and physicists. Okay, so let me just finish. So Well, in the last 30 minutes, we've gone through a journey through the zeta functions, right? But there are many, many other things that can connect number theory and physics, or mathematics in general and physics together. So who knows what is there waiting for us at the end of the road? Maybe some physicists will finally get the $1 million by solving Riemann hypothesis. So that's the end of my talk. Thank you.
Thank you. We don't have time for questions, unfortunately. We don't. We have to move on to the next talk. We don't have time for questions, but
I could stick around. We can talk about
I
it.
would like to make a remark, because this is supposed to be an undergraduate-friendly session. So I would like to make a remark for the benefit of the students that are here, that the analytic continuation of the Riemann series is most familiar to physicists in the context of the Casimir force, as discussed. I mean, being in Amsterdam, you heard of it. As discussed, for example, in textbooks such as Sakurai Napolitano textbook on quantum mechanics, which is used at many universities.
Thank you.
So if you want to see the physics in the more elementary context, just look there.
Thank you. All right, thank you, Miranda. All right, our next and final speaker is Jonathan Hobbs from JPL.
How's the sound? All right. Okay. All right. Thanks, Bo. Very much appreciate the opportunity to participate in this session. Just to kick things off, my educational background is in statistics and atmospheric science. And I think, like the previous speakers, I'm going to sort of bring perspectives from things I do day to day and how that's interfaced with the mathematical institutes along the way, and the benefits that we've gleaned from that. So the title of the talk is Multidisciplinary Collaborations Enabling Uncertainty Quantification for Climate Science. And so as an outline, like I said, I'm going to start with a little bit of an overview of some of the things that I work on at JPL, and motivate that with some of the objectives for NASA Earth Science overall. And then I'll talk about the work I do on uncertainty quantification with respect to NASA science data products. And then I'll bring that into some of the interactions that I've had with a couple of different NSF math institutes, one of them being SAMC, and then the other is IMC. And I'll talk about that down the road. So I'd like to start off with some motivation for a couple of key problems in climate science, and some real challenges now that we're in the midst of a rapidly changing climate system. And the climate system includes numerous interconnected processes that are often represented through computer models. And in order to understand those processes comprehensively, really the expertise has to span across multiple disciplines. So the example I have on this slide has to do with the carbon cycle, and monitoring the carbon cycle due to perturbations, particularly from fossil fuel emissions. So the simple schematic here basically shows these very high-level different reservoirs that store carbon: the atmosphere, the land, oceans, and then the fossil fuel reservoir. And then basically the arrows there are just very rough estimates of the annual exchange rates across those different reservoirs. And then the one on the right is sort of a recent estimate of the contribution of fossil fuel emissions into the carbon cycle. So that, if you look at the numbers, the fossil fuel perturbation is a bit smaller than the exchanges from land to the atmosphere and ocean to the atmosphere. But if you actually look at sort of the net exchange in either of these branches here, the fossil fuel value is sort of comparable to the net exchange from atmosphere to ocean and land to ocean. And in addition to that, the uncertainties in particularly these natural exchanges is also about the same order of magnitude. And so really getting a handle on what the magnitudes of those exchanges are is a really important challenge for carbon cycle science and climate science overall. And so NASA is trying to do its part to help monitor those changes. Another key process in the climate system is the water cycle. The schematic here really shows the complexity that's involved in monitoring the water cycle. Again, you can sort of think about it as these different storage reservoirs within the land surface and the atmosphere, and various bodies of water, including the oceans and freshwater storage. And then there's all of these exchanges across those various different components. They occur at very different spatial and temporal scales, and modeling all these processes comprehensively is a big challenge, as is monitoring them. And really, it's sort of an all hands on deck sort of approach to monitor all of these processes using all available capabilities to do that. And so a lot of what we do within NASA is doing what we can to enable the technologies of remote sensing in particular to help in monitoring the Earth system. Of course, there's a broader science perspective at JPL and at NASA overall, monitoring Earth, monitoring the solar system, and monitoring the universe. Most of my work is in the Earth science realm, so that's what I'll focus on in the discussion here. But the figure here basically shows the in operations and planned fleet of Earth observing capabilities for NASA. And so kind of the way to interpret this here is, if we start on the inner part of the spiral, are some of the longest operating NASA instruments. I'll talk a little bit about Aqua over here, as well as OCO2 up here. And so some of these have been operating for multiple decades now. And then as we get out into the outer parts of the spiral here, I think all of these in green are sort of very recent operating missions, as we call them. And then as we get further out, are planned missions that are sort of in development or planned for the future. There is one update. The first in the orange color here, this PACE mission, just launched, I think, last month, and is working on getting into operations. So as I alluded to earlier, these projects, if you will, are termed missions. They're usually focused on a single remote sensing instrument or satellite, but they're always informed by science objectives. All of these have particular sets of science domains that they want to inform, or science questions that they want to address. And then the development of the capability spans across multiple years, and it definitely spans across multiple disciplines and requires expertise among multiple domains. And ultimately, once these assets are deployed, the directive is to deliver science data products to the public and the science community. And so part of what we do at JPL once these missions are in operation is to execute that pipeline to process these data products so that they can be used by the science community. So in doing that, we kind of have a range of levels of data products, as we call them, that have various utility and various levels of processing for the science community. And roughly speaking, most of the missions group these products into 4 different levels. And as you go up in level, basically, there's additional processing and computation that's typically involved in that process. So at level 1 is essentially the raw radiant spectra that come from the sensors. There's an example from the AIRS mission at the bottom there of what a level visualization of a level 1 product might look like for a single swath on a single day. And then the next level up are derived geophysical variables that basically have the same spatial and temporal coverage as the level 1, but have some interpretability for science. And I'll talk a little bit about how that translation is done shortly. And then there's additional levels of processing to level 3 and level 4 that go on for certain missions and activities. And a key message about this whole pipeline is that at every stage of this process, there is a lot of expertise needed in a lot of different disciplines, a lot of physics, a lot of mathematics, a lot of computer science, statistics goes into all of the various processing levels here. So I'll talk quickly about a couple of example missions that I've been a part of. The first is the atmospheric infrared sounder. That was the image we saw on the previous slide. And then the orbiting carbon observatory 2 and 3, OCO2 and 3. So AIRS is the atmospheric infrared sounder, and this has been operating on the Aqua satellite, which was one of those that's now on the very, very long-term record on the figure we saw a few slides back. It's on the Aqua satellite. And AIRS has been quite valuable for getting climate data records over this now multi-decade mission for a number of geophysical quantities. So as an example, the maps on the right there show basically each point is for a single AIRS footprint on the ground on a single day, estimates of basically the near surface air temperature. I think the top is a nighttime overpass from AIRS, and then the bottom here is a daytime overpass as Aqua goes through a polar orbit. This has been a very valuable record, but actually the Aqua satellite and a few of those other older satellites in the fleet are going to be deorbiting within the next few years, and their records will come to an end. There are other similar instruments in the fleet, particularly for some of these high priority observing capabilities. And so another technology that's really in demand is to make use of these multiple instruments that are observing similar quantities to extend that record in space and time for climate science. And we have some work that we've done that we call data fusion that uses some data science and capabilities to do that sort of estimation. So a little bit more about the observations. Fundamentally, these instruments are basically observing, most of them are passive, some are active, but they're basically observing radiation at the top of the atmosphere in particular bands of the EM spectrum that have been selected for that particular science objective. So in the case of AIRS, AIRS is observing in these little shaded bands here on the figure, mostly in the thermal infrared. And so that part of the spectrum is sensitive to thermal emission from the atmosphere, as well as the surface. And so there's a capability to understand what the vertical temperature profile in the atmosphere is from observations like this. In addition, various gases absorb in different parts of the spectrum. And so AIRS is sensitive to the presence of gases, particularly water vapor, but also ozone, carbon dioxide, methane, carbon monoxide. So all of these are potential science data products from these missions. Now a little bit about OCO2 and OCO3. This is getting back basically to the carbon cycle problem from earlier. OCO2, the ground track of OCO2 is kind of depicted in the picture on the right. And so for a single, each of these spatial footprints in the case of OCO2, each of these little parallelograms here is about 1 kilometer wide by maybe about 2 kilometers long along the ground. And as kind of the figure shows, you get basically this radiant spectrum for each of those individual footprints. And the particular EM bands that have been selected for OCO2 are very sensitive to absorption of carbon dioxide in the atmosphere. And so the goal basically is, given a radiant spectrum like this, can we estimate what the atmospheric carbon dioxide is in that particular location? And if we have then the substantial spatial coverage that the satellite will give us, that can really inform some of those questions about carbon cycle science that we talked about at the very beginning. There's a companion, so OCO2 basically does a polar orbit a lot like Aqua. And then there's a companion instrument, OCO3, which is actually on the International Space Station and has a similar capability. Because of those two different installations, the observing patterns globally are a little bit different, and that's actually very complementary. Okay, so this is sort of a quick schematic of this flow of data products for OCO2 and OCO3 in particular. So for a single footprint, we get a radiant spectrum that looks like this on the top left across these spectral bands that they're observing. And then the goal is to move from level 1 to level 2 is to estimate the carbon dioxide for each of the footprints. And we might be able to map out along a single section of an orbit of OCO2 what that looks like down in the lower left. And then I'll skip over to the lower right, which is then additional processing and computation can be done to then translate those atmospheric concentration estimates into what are called fluxes, which is basically an estimate of the atmosphere-land, atmosphere-ocean exchange of carbon. And as I said earlier, going across all of these various steps definitely involves a lot of physics, math, statistics, computer science at every stage. And what we're particularly interested in a lot of the work that I do is, can we also trace basically the flow of uncertainty across this processing pipeline? It's a really important thing for science, particularly in something like carbon cycle science, as we go from the raw satellite observations to those estimates of carbon dioxide in the atmosphere. What sources of uncertainty are we introducing, and how well can we quantify those? And this is where we really rely on, we've relied on a lot of work that's been done through various efforts, including collaborative efforts with institutes like SAMC and IMSI, and important work in the academic community and in the national labs as well, to get a comprehensive framework for uncertainty quantification for complex physical systems. And one thing we really relied on was there was a a National Research Council report about 10 years ago on this topic that's been very foundational for a lot of work that we do and a lot of related work elsewhere. So let's see. So this is on the next couple slides, I'll just step through a little schematic of the kind of the flow, particularly for that problem of going from the level 1, which is the observed radiant spectra, which is the blue Y up here, to some estimate of our quantity of interest, like the carbon dioxide in the atmosphere. So that's what this little orange X hat is over on the right side. And this figure is just showing sort of a conceptual sort of framework for how this is realized. There really is, there's a target or a true state that we're wanting to estimate, and the radiant spectra that we observe is some function of that true state. And we have some knowledge about that function, but not perfect knowledge. And then there's additional computational processing that's done in our data product production that introduces some additional artifacts. And fundamentally, what we want to do is characterize, basically give probabilistic characterization of the distribution of those quantities. And that involves multidisciplinary knowledge, fundamentally. So this is just a little bit more detail about that. What we actually get, and what a lot of the science data users are interested in, are those level 2 products. In the case of OCO2 and OCO3, the estimate of the carbon dioxide in the atmosphere at each of the satellite footprints. Oops, sorry about that. And what our effort in terms of uncertainty quantification aims to do is to do something about understanding the joint probability distribution of that estimate and the true state. That really helps, that characterizes the uncertainty. And there's a number of complications in there. I think the one that I highlighted here on the slide is in this operational processing. This is really an inference that we're doing, and there's a forward model in here that represents our sort of state-of-the-art understanding of the radiative transfer in the atmosphere and the surface that involves a lot of inputs that we may not know perfectly, and all of that enters into the characterization of uncertainty in this problem. So that's kind of an overview of a lot of the things that I think about on a day-to-day basis. And we've had some very impactful interactions thanks to the NSF Mathematical Institutes. And I'll talk through a few of those in the rest of the presentation here. I do want to make one brief digression, which is to mention, as Bo alluded to earlier, we are at JPL one of several federally funded research and development centers, or FFRDC as they're called. And these are usually funded by a single federal agency and then operated by like a university or some nonprofit organization. So at JPL, we're operated by Caltech. Most of our funding comes from NASA. And so this is just a map of the various FFRDCs and the agency that funds them. So of course, Los Alamos and all of the other Department of Energy national labs fall into this category. Another one that I'll highlight is Boulder, Colorado, is the National Center for Atmospheric Research, which has been instrumental in a lot of the climate science UQ work that's gone on. So I think in a lot of the activities I've been involved in with the mathematical institutes, certainly there's been a very substantial FFRDC presence, and there's been, as was discussed earlier, a lot of mutual benefit in those interactions. The FFRDCs we're a lot of times, as I said earlier, very focused on there's a certain job that we need to get done, and it's a very substantial one, like operating some satellite mission. And so opportunities for research are there, but they need to sort of be targeted towards our objectives. And it really helps to interface with the academic community and industry to know what sort of state of the art is in the research community and how we can engage. And I think, as Danny alluded to earlier, this is a really great opportunity for us to interact with early career interact with early career scientists because we need to maintain our workforce going forward also. So the rest of this here, I just want to highlight some of the interactions with the NSF institutes, and I think I mentioned the couple of the points here on the previous slide, that interactions with the academic communities facilitated by the institutes is really valuable from our standpoint at the FFRDC. So I'll say a little bit about SAMC. So SAMC was the Statistical and Applied Mathematical Sciences Institute, and that operated from about 2002 to 2021, and was stationed in Research Triangle in North Carolina. And the mission that they had, at least most recently, is up there on the slide. I think we heard, particularly from Christian, we heard about kind of the mode of operations was very closely aligned with some of the things that he talked about. SAMC focused on having these long programs. At one point, they were year-long, and they would target workshops and short courses around those. And the other thing that SAMC did was then encourage the community that came together to develop working groups that would then sort of tackle specific research projects over the course of that long program. And we had some very productive activities that emerged from a long program, I think in about 2018 on climate science. And we actually took this level 1 to level 2 remote sensing data processing problem to that working group and addressed a particular challenge with that, say, the OCO2 problem, and extended that level 1 to level 2 problem to incorporate spatial correlation within a small segment of the orbit like this on the upper right. And we were able to get some impactful results out of that and develop a paper. And it really, the methodology in working with remote sensing scientists and spatial statisticians really helped to mitigate one of the challenges in that problem, which is spatially correlated errors in those estimates of the atmospheric CO2. Another working group that I was not a part of that actually spanned across multiple SAMC long programs over the years had to do with climate change detection and attribution. And I think this was a really a flagship activity within SAMC. There was certainly a broader research community that's emerged in the last couple decades on this particular topic. But there were some very impactful interactions between climate scientists and statisticians on this topic that led to some key publications as well, including this one led by Matthias Katzfus in 2017. So then enter IMSI. I've had some meaningful interactions with IMSI as well. The mission is up here, and we've heard a bit about it along the way today as well. And we had in late 2022 a workshop as part of the long program on confronting global climate change. We had a remote sensing for climate and analysis workshop that I was a co-organizer for, and that was a very valuable activity. Again, it was really facilitated some interaction between the FFRDC community, particularly at JPL, and a number of academic researchers who are doing some very interesting things with a lot of different NASA data products. And in addition to that, there were, of course, a number of workshops as part of this program. Another one that I wanted to highlight is basically the torch was passed on this detection and attribution effort, and several of the previous SAMC working group key members organized a workshop with IMSI to bring together that detection and attribution community again to move things forward on that research activity. And I think as others have mentioned, one of the great things about IMSI and the way they've structured things is now all of the recordings of the workshop presentations are available on the website, and definitely worth a look for a lot of these key research areas. So just to wrap up a few remarks about the efforts here and my reflections on our interactions. I think as we've heard, these interactions have seen participation along multiple dimensions, multiple agencies, spectrum of academic participation, as well as a spectrum of career levels, from early career to very senior researchers. And definitely in these climate uncertainty quantification activities, we've seen a lot of representation from multiple disciplines. And I really think this does benefit us at NASA and JPL, both in the short and the long term. We got some publications out of some of these activities, and they've led to continuing and ongoing collaborations and things like grant proposals and that sort of thing. And the IMSI collaborations are moving in that direction as well, so I'm very encouraged to see that. And we've even sort of pushed this into the realm of some things through JPL, including their Center for Climate Science. So that is all. Thank you very much. Glad to take any questions.
Thanks, Jonathan. Before we take any questions, I just want to make sure that we thank the Forum on Physics and Society and the Division on Computational Physics for co-sponsoring this session. So if there are any representatives from those organizations here, thank you very much. And do we have any questions for John? Yeah, come up to the mic, please.
Hello.
Hi.
I'm Lauren from BAE Systems, formerly Ball Aerospace. And I have a question for sort of the interaction between these institutes and maybe the remote sensing builders. So in particular, I spend a lot of time in level 1 dealing with radiometric uncertainty and spectral uncertainty. And I was wondering if you could speak to these physical models and quantifying the uncertainty. So I tend to think of requirements as, look, I can build what I can build. Yeah. This is the uncertainty associated with counting those photons. So I guess, is there a path back where somebody could come to me and say, hey, actually, if you could get it to this uncertainty, then we can unlock all of this new science? Yeah, that's a great question. And I think the fundamental term there, at least in NASA speak, is science traceability. And I think it's basically what you said. You may, depending on where you might start at two different ends of the spectrum. You might start with, I want to estimate fluxes of carbon between the atmosphere and the land to a certain precision. And then there should be a way to trace forward then to, that needs to trace through based on the knowledge we have to a certain precision on the instrument, on the photon counts themselves. And that's basically tracing through that level 4 to level 1 pipeline, essentially. And the NASA missions are supposed to address this in their formulation stage. It's not always that very clean. In fact, it's rarely very clean. But that's something that they definitely put an emphasis on, and I think going forward, it's going to be even more critical. Particularly when then you want to bring in additional considerations like
Well, but I already have 4 or 5 other satellites from NASA and other organizations around the world that already observe this. What value added will I get by this instrument? And that needs to be factored in sometimes as well. Thanks for the question. Yeah, go up to the mic, please.
So you have these instruments that are all hosted by NASA, but there's also data available from foreign countries, like for example, Europe. Can you use that data in some way over long term to actually calibrate your uncertainties independently?
Yeah, that's a good question as well. Yeah, I think there's another figure that I've often used in this talk for the greenhouse gas sensing enterprise. You take a few instruments from NASA, and on top of that, there's several times that number from various other organizations and from around the world. And I think the science now is at a point where there's capability to use all of those data products in concert. And one of the key sticking points in the carbon cycle problem in particular is ensuring that the various satellites, even OCO2 and OCO3, which are separate instruments but the same technology, is making sure that they're sort of in harmony and they're seeing the same planet, if you will. And that's one of the sticking points with that effort. But that's definitely an area of focus right now.
Do we have time? We have time for one more question. Okay, well, thank you everybody for attending the session. Thanks, John. Thank you all, the speakers, one more time. And that concludes this session.